time.
Yeah, that's okay because my presentation's better than his.
Oh, good, good. I saw the look. I did. Well, guys, welcome back to Science of Diving. We went through, we're kind of jumping around a little bit, and we're a little farther in, but we're going to have to do a little backtracking today as well. Today we are going through, I'm going to go ahead and share my screen if that's okay with everybody. Start, present, share screen. I think it comes up with a tip every time. Let's see. I'm just going to share everything on that screen. I think it'll be easier. There we go. There we go. So we are in Science of Diving. So just I took down notes. The presentations that we have are Archimedes. One of my favorites, by the way, Jolene, that I really like the story Archimedes. So I'm excited to hear your presentation on that. Aaron, you've got saturation, desaturation model. So that'll probably be the next class. Dallin, I'd like to see if we could knock out DCS tonight, if you wouldn't mind. Dwayne already did dive maladies, and I think would everybody feel comfortable giving Dwayne at least an A?
Yes.
Yeah.
I think he deserved an A.
Yeah.
A plus? Are we pushing it with the A plus, or do we?
I think you're pushing it.
We'll go for A. Oh, I know who we're missing. We're missing Donna. I'm gonna text Donnie real quick. Are you? I knew I was missing somebody. Joining SOD.
So it looks like we weren't the only ones that forgot.
There we go. It happens. It absolutely happens. This is Saturday night. It's a weird night for a class. It's a night that I don't generally do class on. All right. And by the way, I'm hoping after I talked with Christina Zanato the other day, I made a commitment, and I hope you'll join me in it, that I don't use single-use plastic bottles anymore. So you see me using a single blank, you can get after me about that, but I don't. And then I don't use restaurants that use plastic silverware anymore. I actually, in my backpack, I've got a set of utensils that's like a travel set / camping set. So if I do need to go somewhere that does have that I need utensils, I carry my own and I wash them afterwards. So we're trying to save the planet imperfectly at best, but do our best. So thus that. So let's see. I haven't heard from Donnie yet. I'm going to go ahead and move through this. And if we have to catch up with Donnie, we will. Absolutely. But let's see. But I want to reiterate where we're at. So what are physics? Let's just jump into it real quick. And we're going to get to Archimedes here pretty quickly. So what are physics, guys?
Well, a lot of things I do not understand well.
Okay.
They're the way objects interact with each other.
Okay. I'll accept that. And who else got Dallin? What do you think physics would be?
So it'd be a way anything interacts. So as far as like dealing with science of diving, wouldn't it be the way that the gases interact as well as not only just your body?
Absolutely. Who thinks that's a good expression as well? Okay. And finally, Jolene, what do you think? What's your take on physics?
You know, I am not going to lie. This is really hard for me. I do not understand a lot of it. I understand the principles behind it, but like the dive principles, like how you're supposed to use it, but it is very much over my head.
I doubt that very highly. You're highly intelligent. So simply defined, physics is a study and characteristic of interaction between matter and energy. And energy that impact or they're important to understand. So physics is often called a qualifier, quantification to precision of the science. So it's how we measure things like the partial pressures that we deal with. That's absolutely physics. The pressure on our cylinder, that's physics. The idea that Boyle's law, for example, as pressure increases, volume decreases. As volume decreases, volume increases, right? It's an inverse law, which is Henry's law, Charles' law, Gay-Lussac as well. All pretty much the same idea. They took different portions of that, but it's all the same idea. Marriott, same thing, right? Even Henry's law falls into that to a certain degree. So the idea is that you take a Scuba cylinder that's 80 cubic feet, and you take it to 33 feet down, how many cubic feet are left in that cylinder, Dallin?
Sorry, say that again.
Mr. Dallin,
Oh.
did I lose you?
Yeah, sorry, my phone kind of paused.
I think we lost Dallin. Okay, how about Aaron? Aaron, what do you think? 80 cubic feet at 33 feet down. What's left? Aaron, you're on mute.
Sorry, 40 cubic feet
40 cubic feet. Why?
because you've doubled the atmospheric pressure.
Absolutely. So if you double 50% pressure change, takes it down to 40 cubic feet. So if we go to 66 cubic feet, or sorry, 80 cubic feet at 66 feet, where are we at, Jolene?
So 66 divided by 33.
Hey Ben, can you hear me?
23.
I can. There we go.
Would it be 23?
What was your question? Your question is, what's the
60.
pressure?
How
Or-
much? What's the how many cubic feet do we have at an 80 cubic foot cylinder at 66 feet?
So you're just using Boyle's law, right?
Correct.
So what?
So is that the one that goes 33, 66?
It's pressure times volume is equal to pressure times volume 2.
And you're doing
Right.
sorry, we're having a little trouble with the math. So you're saying, tell us what the pressure and the volume are again.
80.
All I'm looking for is the cubic feet of cubic foot equivalent of the cylinder at 66 feet. And I give you, here's the hint. So the 33 feet, we have a 50% pressure change.
Mm-hmm.
At 66 feet, we're 1/3 the volume. At 99 feet, we're 1/4 the volume. At 130 feet, we're 1/8 the volume. At 150 feet, we're the volume. So literally, it's just going to be 1/3 the volume.
80 divided by 3.
26.
26.6?
Or
There you
27.
go. Yeah,
Okay.
absolutely. So right there. So simple enough. As we go down, we don't change the size of the lungs, or nothing else changes. What ends up happening is we have twice as much compression in, and so we're able to reduce the amount of gas in because the gas is literally compressing into itself. Think of a tin can, right? You take that tin can, it occupies 12 ounces of total space. I stomp on that with my foot. Now it's 1/8 or 1/16 the value amount of volume space, right? That's basically what's happened is as the atmospheric pressure around it is compressing everything around it, it's taking up a less volumetric space within our universe. And that's how partial pressure works as well. Overall, is the idea is if I have a molecule that's certain size and diameter, right? If we look at this and we say, whoop, that took that to fill screen. Let me work on the right screen here. So we've got, let's say this is our molecule, right? Well, that didn't work. So this is our molecule in space that we're working with, right? This is one molecule of oxygen or air, 21% nitrogen, or 21% oxygen, 79% nitrogen, right? As we go down and we start compressing that, all of a sudden it is half the size. Does that make sense? As it's compressed down, it's still 21% in that molecule size, and it's still 79% nitrogen in that molecule size. But now the same molecule is taking up half the space. So two molecules are now taking up the same space as one normal molecule. Now, where that comes into play is as it gets smaller, it's able to absorb into our tissue that much more easily because it's smaller, right? So we know that BBs go through a grate much easier than marbles, right? And marbles go through a grate much easier than bowling balls. That's how profusion really works overall, is as the molecules get more tight and smaller, they're able to agitate faster. They're able to fit through the grate, if you will, much easier. And that's not really what perfusion is. The only other part of perfusion to really be aware of in that idea is that it also is controlled with temperature. Warmer, oddly enough, now this works a little bit differently, and this is Henry's law for you, is that as the bloodstream gets warmer, and as the molecules get warmer, they don't excite as easily into the tissue. As they get colder, they're able to slide, if you will. They're able to be more excited into the tissue, and they will actually perfuse faster at a colder temperature. It's one of the interesting reasons that Henry's law comes into play when we start doing cold water diving, is because as the molecules get colder, they perfuse into the tissue more easily. So it's an exact opposite of what you would think. You would think that as something gets warmer, that it would perfuse faster, but it's not. In Henry's law, as things get colder, they perfuse faster. Now, if things
I think that the reason that is, if you go to like thermodynamics, colder air molecules are closer together, where warmer air molecules are further apart. So it's harder to get into the tissue because they're
colder.
taking
That's exactly
bigger space.
That's a great explanation, and it's exactly right. But as you look at it on the surface and you start thinking, wait a minute, colder moves faster? No, it's because it's more tightly compressed and it's able to make it through that grate more easily.
Warmer moves faster.
Yeah,
like warmer moves faster. Yeah,
warmer moves faster. But you'd think with warmer moving faster that it would perfuse faster as well, but it doesn't. Warmer because the molecules are spread farther apart.
Yep.
You're absolutely right, and that's the exact reason. Good job on that. So overall, now here's our question for the day. If gas perfuses into the tissue, what is the process that's called when it's coming out of the tissue? There's a specific term.
Diffusion? Is that what
Diffusion is ding, 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 ding. Look at the MD using his education. I like it. That's exactly right. So if it prefuses in, it diffuses out. Right. And so as it's diffusing out, it comes out of the blood, out of the tissue. Now, the neat thing is Bowman theorized that there was originally, his first theorization was that there was 4 tissue compartment models. And then he said, whoa, very quickly, he changed that. And he said, no, there's actually 8. And then a few years later, as they were studying it, he realized that was not granular enough to explain what was going on in the tissue compartments and the cells and within our body. And so he revised that to Bowman 16A and said there's 16 compartments. Then he realized that, wait a minute, not all compartments are going to diffuse or prefuse at the same rate. Kind of brilliant thinking, right? That if all 16 tissue compartments, divided by 100, whatever that works out to, 8, perfused at 8%, that would be great. But the problem is we realize and we know that that's a perfect model on an imperfect subject. We're not perfect, and our bodies will never align in a perfect way. So he came back and he says, wait a minute, that can't be correct. So let's change the model, and let's change the model for slow tissue. Slow tissue will perfuse slower than fast tissue. And then he came back with one more model after that a few years later. And so he came to Bowman 16C. And oddly enough, in his 16C, he actually realized that slow tissue had to be divided into 2 parts, tissue compartment 1A and tissue compartment 1B. And then there was 15 more compartments after that. So interestingly enough, as we go through this, we realize that Bowman, we talk about it being 16 tissue compartments, but in truth, we've divided the first tissue compartment in half. So we're basing our algorithmic model on 17 tissue compartments. Now let's talk about that. This is theory, right? And there's not really, you can't say that, the sinew of the body falls into tissue compartment number 4 always, right? Or the fat around my belly is always tissue compartment 1A or 1B. You just can't do that. It just is what it is. So this is a theoretical idea of how things work, right? Sorry, Lucy's going nuts because mom brought food home. So, so as we go through this, we start looking at there's a different perfusion rate for different tissues. But what he's trying to tell you with tissue compartment 1A and 1B is that's fat. It takes longer for slow tissue to uptake nitrogen and the partial pressures than it does fast tissue compartment 16, which would be like the brain stem, the brain itself. The brain is able to get oxygen and get partial pressures of oxygen through our bloodstream faster than, say, my big toe, right? If that, just to kind of make a kind of a visual for you. And the way my stomach or the fat around my waist absorbs that nitrogen is going to be much different than how my brain absorbs oxygen and nitrogen and the partial pressures of what we're doing. Now realize, as we're talking about these partial pressures that we're breathing in and breathing out, breathing in, breathing out, that our body is designed to be in equilibrium with everything around us. Dwayne, would you say that's pretty accurate statement?
Oh, absolutely.
Absolutely. So, Jolene, so as you're living in San Diego because you love the beautiful sea and you love the 60-degree summer and the cool breezes, but you got into marathon running, and you decided, I would really like to run a marathon in Yellowstone at 7,600 foot elevation. Easier to do, harder to do?
Harder.
Why?
Because you're at a higher altitude.
Mm-hmm. Continue. You're going the right path. I like it.
What's thinner?
Oh, well, the air is thinner.
The air is thinner, absolutely. So the molecules are more spread farther apart. So while the percentage of nitrogen and oxygen are still the same, they're always 79-21, right? They're spread farther apart. So the equivalent of what our body needs is farther apart. So it's equivalent for us to be breathing at 7,900 or 7,600 foot elevation, the equivalent of, truthfully, about 19% oxygen. 18 to 19 depends on atmospheric pressure and a few other things, but we'll just use 19. So we're used to breathing 21%, but in this new space, we're breathing 18 to 19%. Our body's used to 1, we're getting a different, right? Now, what happens if you live in Yellowstone for a month? Would it become easier?
Much easier.
Yeah, absolutely. Why?
Well, I would say you get accustomed to it.
Absolutely. Equilibrium, equilibration. So you're equalizing, or you're becoming acclimatized to that. The partial pressure of the air that you're breathing has equalized out, and your body's gone into equilibrium with everything around you. So now your body's has perfused itself to that now equivalent of 19% oxygen. Now, the exact same thing as we go up, the same exact thing happens while we go down. As we go down to 33 feet, all of a sudden our body has to equalize to a new partial pressure. So, Dallin, at 33 feet, what is the partial pressure of oxygen in the air that we breathe?
So at 33 feet?
At 33 feet.
So if we're at 21% and you're at 33, then it cuts by half. So wouldn't it be, 10.5?
I'm sorry, say that again?
10.5?
Nope, you're going the wrong way. While
going up 33 feet.
You're diving to 33 feet seawater. What is the partial pressure of oxygen in the air that you breathe at 33 feet?
Oh, so it doubles. So that'd be 42.
Exactly. So the nice thing is you can get down to just about any depth relatively. There are certainly points where the work of breathing it becomes impossible based upon the weight of the air. And as you guys realize, anybody ever notice the weight difference between an empty 80 cubic foot tank and a full 80 cubic foot tank? Quite a bit of difference, right? Well, the same thing happens when you're breathing. The weight of what you're breathing will get to a point that you can't breathe it. It's too heavy. Your lungs are not able to process it. So one of the things they do, and this is one of the reasons, there's another bigger reason why they do it, but a lot of times what they'll do is they'll cut it with helium to make the air lighter. So you're able to breathe it. So you actually breathe it in. Now, where that becomes a big problem is sat divers who are going down to 1,000 feet, and they're trying to work at 1,000 feet. Even at 1,000 feet, helium becomes too heavy to breathe. And so the latest test that they're doing on that is to try hydrogen. Hydrogen is lighter than helium, and they're doing a hydrogen mix in that process. So there's your interesting trivia for the day, that air becomes actually too heavy to breathe. But as we go through this process, just like we were talking, to kind of back up, that if we get to an equalization at 7,600 feet and we're able to be fine again, same thing will happen at 33 feet, 66 feet. Our body will get into equilibrium with that. Okay. Now, the magic thing is as we come up from that, the nitrogen is going to start diffusing out of our tissues, and it has to go somewhere. So the first thing is that it goes where? Dwayne, where does the nitrogen go?
Well, doesn't it diffuse out of your tissues and into your lungs, and you breathe it out, right?
Absolutely. Bloodstream, and then in your lungs, and the whole process, the circulatory system, lungs, and it's exhaled. But the challenge is you can only allow that nitrogen to come out at a certain pace. Nitrogen is one of the big precursors and big scary things that we have to deal with, because as it comes out of the tissue, it comes out of all your tissues at different paces, right? It comes out of my slow tissue much slower than my fast tissue. It'll come out of the brainstem much faster. So we have to make sure that we're rising slowly enough in the water column, and we're allowing that time to allow that nitrogen to come out of the system in a partial pressure. So as we equalize out, it's one of the neat things. That's why we use pure oxygen as a deco mix in diving, because what ends up happening is it literally flushes just like a toilet. I mean, think about it. If you flush bad stuff out, right? That's what pure oxygen does, or higher percentage of oxygen, is it's bathing your bloodstream, you're bathing your tissue compartments, bathing your whole body with this higher percentage of oxygen, lower percentage of nitrogen. So your body's trying to equalize to that, and it flushes it out more easily and a lot more quickly. It's less dilution. Remember, the solution to pollution is dilution. I think I've heard that somewhere. So that's why we use pure oxygen, or we use nitrox in diving, because it dilutes the nitrogen down so that it doesn't become quite as big a problem. Does all that make pretty good sense?
Yes.
Good. How about you, Jolene?
Yes, I get that. I understand the principle. Thank you for asking.
Okay, I want to make sure. You said you were having a hard time with this, so and I'm trying to break it into simpler terms for you to make sure you get it.
Thank you.
Overall, that's the idea of what we're dealing with in physics. And physics is our way of measuring all that in a way that we're able to understand and put together a litmus measurement on it. If we can put some sort of measurement on it, we can say, okay, if my car goes from here to there, how fast did it go? Okay, with 50 miles an hour. And I can tell from that point on that 50 miles an hour is a safe speed, a not safe speed, a conservative speed, a non-conservative speed. I can start putting some measurements on that, because I can say, okay, 10,000 cars drove from here to Pocatello at 50 miles an hour, and none of them had accidents. Okay, that's safe, right? We could probably reduce the conservativeness a little bit and see what happens. Well, let's see what happens when we send 10,000 cars from here to Pocatello at 70 miles an hour. We still had no accidents. Okay, but that's what physics is it's the study of that. And what we as scientists do is we go through, we start measuring and putting together information based upon what we know, and we say, okay, we did this X amount of times. Now, it's interesting to note how we figured a lot of this out is through the Navy. And as fair or unfair as it is, the Navy literally takes, and they do this on a regular basis still, Naval Experimental Diving Unit, and NEDU in Florida. God bless them, because they're a bunch of wild and crazy guys for sure. What they've done in the past is they'll literally take 100 guys, and they'll say, okay, we're sending 100 divers to 130 feet. We're going to leave you there for an hour. And then we want you guys to, we want the first batch to 50 for you to ascend at 60 feet per minute and not do a safety stop. And then we're going to measure the gas in your arterial blood work. And we're going to say, that was good or that was bad. Don't worry, we're going to have a pressure chamber. So if you start having symptoms and vomiting and narrow vision and things like that, don't worry. We'll throw you in a chamber. But that's literally what they do. They literally do physical tests of this. And then they go back and they also study actual diving accidents as well. Now, it's worthy to note at this point that there are several companies that have come out with personal Doppler radars that you're able to purchase. Nikki and I have one. It's called ODive. Very slick little unit. And what we start realizing is that you can certainly build an algorithm and a plan based upon 119-year-old, perfectly good, physically fit young men who are used to getting up and running 5 to 6 miles every morning, and Dwayne, you and I know that those kids can eat a box of donuts and lose 5 pounds, little turds. But you and I, unfortunately, cannot. So basing the algorithm and the studies and the information based upon their information is a bit faulty, right? It's like trying to judge my the quarter-mile race of a Corvette versus my Dodge pickup. It's just they just don't compute, right? My Dodge pickup will never keep up with a Corvette, as much as I would love to say it would. And so that's one of the things we do is as we go back and start studying dive accidents. And one of the nice things with these new personal Doppler radars that you're able to purchase, if that's something you're interested in, is you're able to go through and start doing your own dives. And then 30 minutes after the dive, you're able to come back and measure the gas bubbles in your arterial gas network. And when you do it twice, and then plug your dive computer in, and it'll start giving you an idea. Wait a minute, your bubbles are too much, or wait, oh, cool, your bubbles are a lot less. And so as we've become more technologically advanced, we've been able to add really neat things like personal Doppler radars to the mix, so we can get an idea. How does your dive compare to my dive, compare to Aaron's dive, compare to Dwayne and Jolene's dive? And I can promise you, Dwayne and Jolene, your dives and how the gas interacts and works with the two of you is extremely different. And no matter how much you guys kiss at night, I promise you, the feeling for both of you is a little different, right? It is what it is. And Dallin, same thing with you. I mean, the way you articulate gas through your system and perfuse and diffuse is going to be different than how I do it. I've been pretty blessed that in this process, that because I dive a lot, I've been able to build up a repetition ability, and nitrogen doesn't seem to affect me quite as much. I read a study about a diver. His name was Sheck Exley, and they did a bunch of studies on him. And the doctors determined him to be excessively nitrogen resistant. Now, it is noteworthy to say that he did die in a cave at 800 feet, trying to break a record in a cave. But he also held a whole bunch of records, air dive records, where he could dive to 300 feet on pure air without getting nitrogen narcosis. So how he processed nitrogen and how I process nitrogen are still very different. So that's the idea of physics and overall. Does that make sense, guys?
Yes.
Perfect. And one of the things as we go through this, I don't want you to guys let the math intimidate you. Physics is simply a scientific way to explain what divers experience on their dive. That's all we're really trying to tell you. I'm going to throw some formulas at you guys. I'm going to throw some hardcore stuff at you. Henry's Law, Boyle's Law, Charles' Law, Gay Lussac. I'm going to throw a lot of those at you, and then because I have to. But I want you to at least get the exposure to it. But then we're going to back them out, and I'm going to explain it to you simply. And how does it apply to you as an individual? So please don't get too worried about it. So overall, again, physics are the measurement of pressure, atmospheric pressure, hydrostatic pressure, gauge pressure, and absolute pressure. Now, here's a magic question for Dallin today. What is the difference between gauge pressure and absolute pressure?
So absolute pressure would be the pressure at surface. And then as far as gauge pressure, the gauge pressure is gauging and either reducing or allowing more pressure as you ascend or descend.
You're on the right track. Absolutely. So gauge pressure is absolute pressure minus 1. So absolute pressure is the total pressure of everything around us. That's just like it sounds. So absolute is everything that we see, everything we touch. But once we get below the surface, the gauge pressure has to start measuring the amount of pressure exerted on it by the hydrostatic forces around it. So for it to get an absolute correct reading of gauge, we have to minus 1. And what we're doing is we're minusing out the surface tension, the surface pressure, so that it'll measure the actual pressure of what's being exerted on it as an individual. Does that make sense?
Yes.
Perfect. Yeah, it's kind of like taking a survey on a house or on you and counting you and your significant other as one person, right? we've got to, once you get below the water, you have to be that individual. You're by yourself and one individual person. So my magic question for you, and I have a lot of magic questions. Jolene, when is a scuba cylinder empty?
Well, you don't want to. Well, I guess I don't know, because I know you're never supposed to take it down to 0%.
Sure, but outside of that, when would you consider a scuba cylinder to be empty?
Like at 1 atmosphere? Is that? I don't know. I'm sorry, I don't know.
No worries. When would you the Coke? I don't know. Do you drink Diet Coke or Pepsi or root beer or anything like that?
Yeah.
Okay, perfect. So we'll say A&W root beer. That's my favorite. So when is the A&W 2-liter container empty?
When it's gone, there's no more left.
Perfect. Or when I take the top off and I try and pour something out and there's nothing coming out, the pressure inside is equal to the pressure outside.
Oh, okay. Okay.
They're in equilibrium. There's just nothing in it, right? We would consider a scuba cylinder to not be empty if it had 10 psi or even 1 psi. If I open it up and it made any sound, it would be considered to have at least some gas in it. Whether it was sucking gas in or pushing gas out, it would be considered to have either a positive or a negative pressure. Correct?
Correct.
Okay, there you go. So that's what a scuba cylinder is empty. Absolutely. Now, if I took a scuba cylinder that was completely perfectly empty at 0 feet elevation, atmospheric level 0, and I took that cylinder up to 16,000 feet, what would happen?
You're gonna have a little bit of pressure in there.
Absolutely. Positive or negative?
Positive.
Sure.
Yeah.
Yes.
Yeah. Because you come up, that's why you always keep that regulator in your mouth. Because as you come up, there might be a little bit of air expansion in your tank.
Okay. All right. You have half the atmospheric pressure at 16,000 feet. By the way, that might be a test question. So absolutely, as you come up, it's going to create additional pressure inside as you go up. You take a bag of chips from here and you go over the pass or get in the airplane, it puffs up, right? That's the effects of atmospheric pressure in a real and meaningful way for you guys. All right. So, if you take a sealed scuba cylinder that is empty at sea level at 16,000 feet elevation and open it, what will happen? We talked about that. I forgot that was the next question. I used to be able to look straight at the my PowerPoint presentation. I decided to look at you guys instead. It was more fun. Let's see. There we go. All kinds of cool presentation dynamics in this. So when a scuba cylinder is empty, your scuba cylinder is empty when the pressure is equal to the absolute pressure around it. There is a difference in the pressure for air to the flow out of the cylinder. So there's got to be either positive or negative pressure within the scuba cylinder. Now, interesting enough, to give you a real practical application of this, last year I was teaching a solo dive course, which is what I love to teach, and I encourage teaching it, or you guys taking it. It's definitely a fun course. At least I have fun. So I don't know about you, but I have a lot of fun with this course. But the idea is that I teach you to be self-reliant of other people. Well, I was finishing up at the end of a dive, and I had plenty of back gas, but I was also carrying a pony bottle with me, a 30 cubic foot pony bottle. And I needed to breathe it off because I needed to have it hydro tested and visualed, and as well as refilled with a new gas, right? So I decided, what better way to take that down rather than waste my good 60% nitrox that I had in it, but I'll just breathe it down. So I went ahead and I was breathing it down. Now be aware, this is all a controlled environment. I'm trained in this. I had another regulator around my neck with plenty of back gas. So at 66 feet in that area, I breathed it down to where it literally went, and there was nothing left. And at that point, I went ahead and called for my ascent, and I took an ascent to 15 feet from 60 feet. Magic question for you today. Aaron, how many breaths? You know the answer to this. I can't ask Aaron. Dallin, how many breaths did I have left that I got from 66 to 15 feet?
So from 66 to 15, and you took one breath, so then you would have, let's see, 30. So
Yeah, it depends on how much
At 15
long.
feet, it's going to increase.
Yeah, it increased up. So I got about 3 breaths out of it. So now my lungs are
Okay,
about
so
2
I was
liters.
close.
Yeah, my lungs are about 2 liters, 3 breaths. So that's at 2, 4, 6. So I got about 6 liters of additional gas from a tank that I breathe to zero out. So this is one of the interesting things that SSI says. If you're on an out of air emergency ascent, okay, you're doing emergency swimming ascent where you have no gas, you can't get your buddy to air share. SSI always encourages you to leave the primary regulator mouth as you ascend. As the pressure decreases, the volume is going to increase and air will start to flow. It happens. I promise you. I've tried it myself just to prove that Boyle was right and that it would save my life. So one of the really cool times that got to prove Boyle's law was accurate. All right. Too many screens. All right. So overall, I encourage you to take a look at this in your book. We've talked about atmospheric pressure. We've talked about hydrostatic pressure. Take a look through this and just get some basic ideas. Now, if you were ever going to burn a couple of numbers into your brain to make your life that much easier in SSI, the bottom numbers I would burn into my brain like it was, and just these numbers right here. Freshwater exerts 0.432 pounds per square inch per foot. Saltwater exerts 0.445 pounds per square inch per foot. I can promise you, this is one of the most common questions I've seen. I've easily seen this in 6 different courses, if not more, through SSI. So Don,
Are we supposed to be seeing that on a slide, Ben?
I'm sorry, say again?
Are we supposed to be seeing those numbers on a slide?
Are you not seeing the slide?
I see water physics still.
Oh, well, let's just represent. Thank you for letting me know. Hey. There you go. Can you see that now?
Yes.
All right. So you should see down here at the bottom, 0.432, 0.445. Don, your question of the day. Why is there a variance between those two, and why is one bigger, and what makes it bigger?
With salt dissolved in the water, the density is higher. Salt water is then heavier than fresh water.
Absolutely. It creates more and heavier, obviously. I step on a can, I squish it so much. If you step on a can, you might squish it less because you're lighter than I am. You would exert less pressure.
Right.
Exactly. So if I were to write anything down, 0.432 and 0.445 would be 2 numbers that I would burn into my brain, because as we go through these SSI courses, I have easily 6 times. All right. I'm going to skip. Does anybody need to go through a refresher on distance and 1 foot equals 12 inches? I'm just kidding. There's a bunch of these that I like to skip. Gases related to diving. We all know that nitrogen the air we're breathing is roughly 78.08% nitrogen, 20.94% oxygen, 0.93% argon. Too bad we can't pull that out of the air and put it in our tanks, because that'd be awesome and a nice little pony for dry suit diving. 0.03% carbon dioxide. Other gases about xenon, radon, vion, everything else is about 0.02%. For purpose of all these classes, we're going to stick with 79-21, if you don't mind. All right. So gas laws pertaining to depth of divers. What is this? What law is this? That P1 times V1 divided by P2 equals volume 2. Anybody know what that is?
Boyle's law. Boyle's law.
It is Boyle's law, basically, yeah. Overall. The good news is most of these laws, Boyle's law, Gay-Lussac, Charles' law, they're all basically the same law if you really look at it. One talks about volume, one talks about area, one talks about pressure. Is there really a difference, truthfully? I say no. So overall, we talked about Boyle's law, and Boyle's law is pretty straightforward. It's easy enough to remember that at 33 feet is 2 atmospheres times 1 equals 2. 99 feet is 4 atmospheres, which is 2 times 2 equals 4. So as we keep going down, we keep increasing atmospheres. So the easiest way to remember that, 50%, 33, 25, and so on. So half, third, quarter, eighth, 16th, 32nd, and so on. Pressure change. So what's the difference between Boyle's law and Gay-Lussac? Well, here's the long answer for that. The simpler definition is basically that Boyle's law, volume is directly related to pressure at a constant temperature. Now, interestingly enough, Boyle, as he was doing his studies on this to figure this out, he was testing on snakes. He was a crazy Scottish guy. And he was not concerned about temperature at all because he was running around in a skirt with no underwear anyway. So he was a little on the crazy side as he threw snakes and containers into the ocean. So I think Boyle was just a little on the crazy side. The smarter guy, about 7 or 8 years later, was Marriott. So Charles Marriott came up with the same law, but he was studying plants. But what he realized is that it had to all be at a constant temperature, because we realized that as temperature changes, volume changes as well. And that's also what Gay-Lussac came up as well, is that the volume is directly related to the temperature. So if I have a container sitting on the stove and I start putting heat on it, it's going to expand and it's going to create more. If I take that same container and I put it in the fridge, it's going to be less. So Gay-Lussac, the big definition, really difference is Gay-Lussac really studied the amount of pressure differentiation when it came to temperature as well. So the golden rule of diving is never hold your breath, and that is directly tied to Boyle's law. Now, another law we're going to talk about a little bit as well is Dalton's law. Dalton's law is used to calculate the maximum operating depth, Beck's mix, partial pressure calculations for gas blending. So question, knowing that pressure and volume are directly related, how would this affect the amount of gas you need at a 99 feet versus 33 feet? Dallin?
So let's see, 99 feet.
Well, you'd need 3 times the gas.
33.
I heard the answer.
So 3 times, well, yeah, it's 3 times the gas.
Because it doubles every atmosphere.
I'm trying to figure out. Okay. Yeah. Okay.
Yeah, that's right. Absolutely. But why? Why would that be? Why would you need 3 times the gas, 33 feet to 99 feet?
Because at 99 feet, you're going to be more condensed versus at 33 feet where it's more freely, what's the word I'm looking for? It's lighter at 33 feet.
Okay. Yeah. There you go. So adding to this, Aaron, what's the effect of this warm water versus cold water? And why?
Warm water, you'll have more, or you'll use less gas because it's more excitable. Cold water, it'll shrink the space between the molecules, so you'll breathe more.
Does everybody buy that?
Yes, because that's basically what we talked about at the beginning of the class today.
Yep. There we
The
go.
absorption.
Absolutely. So interestingly enough, I don't know if anybody else has done this, but one of my favorite things to do is in the middle of the winter is when we go to Belmont Hot Springs, is I like to take my tank, get it nice and full at the shop. I'll fill it up to 3,500 PSI. And then I throw it in the back of my truck and drive 2 hours where the wind chill is probably negative, 5 degrees all the way down. As soon as I get there, my favorite thing to do is get my gear put together and get my butt in the water because it's cold. But I like to go check the platform because it freaks my computer out. On a 117 tank, for about the first 3 to 5 minutes of that dive, I actually have a negative sac rate instead of a positive sac rate. It'll actually, I'll watch my sac rate literally start out at 0, and then it'll look like I'm actually putting gas back in the bottle. So I'll watch my PSI actually increase as I do the dive, which is kind of fun to watch. See your gas at the beginning of a dive be 3,100 PSI, and then increase to 3,200 PSI after being down for 4 or 5 minutes. That's just fun, stupid diver humor right there. So, but why is that? Why does that happen, Dallin?
Because as you go down, it becomes heavier, and so your amount of gases per square foot is going to increase.
Yeah, as it gets colder, the molecules compress in together, right? They get closer in.
Yes.
Everything's becomes more dense, right? Fun fact for you that when I was drag racing a lot, we used to stop by before we got to the track, we used to stop by the store and fill up 5 or 6 big coolers with bags of ice. And what we do between runs, we'd literally pull the car around, we'd pop the hood, and we'd take a bag of ice and we put it on the manifold of the engine to cool it down. And that way it had denser gas that would get into the cylinders, and it would actually go faster because it was able to get more air into the cylinders. So kind of a fun little racer trick for you for the day. So Charles' Law, does this look familiar to anybody, Dwayne?
It's the universal gas law with like the volume held constant here and the pressure held constant on the second one.
What other law does this look like, though?
It looks a little bit like Boyle's law, but
absolutely. So the cool thing is that's what I'm saying is Gay Lussac, Charles, and Boyle were all studying the same thing and independently from each other, and Marriott as well. So I like adding Marriott because I feel like he deserves his cool recognition. So overall, as you guys look at these, it sounds a lot more complicated than it is. And that's one of the things that I've discovered with all doctors out there. No offense, Dwayne. But, Jolene, have you noticed that he has the propensity to be able to make everything sound 10 times more scarier and more complicated than it really is?
Actually, I have to say that he is very good at putting it into people's language, but he has the ability to talk in the higher, like.
Oh, good. Well, that's good. That's very good, because every doctor I go to, you've got a complex neo, and man, you lost me at complex, man. And that's the same thing with these scientists. Truthfully, most of them were studying the same basic idea. They were studying the things independently, and we put it together, and they want to say the same thing. One of them wants to talk about pressure. Another one wants to talk about volume. They're really all saying the same thing. Overall, as you increase pressure at a constant temperature, volume decreases. As you decrease volume at a constant temperature, pressure increases, right? It's an inverse law. If you stick a freaking Bunsen burner under your cylinder, you're going to have more gas in that cylinder because it's in an excited state. That's all we're really saying. As things get hot, you get more volume. You get you take a 3,500 cubic foot cylinder or 3,500 PSI cylinder, leave it in your car in Phoenix at 120 degrees and it explodes. It's because it overexpanded, right? Duh, right? We have to put more air in our tires in wintertime because it's cold. That's all we're really trying to say. It's really awesome how they want to overcomplicate all this to the nth degree where we don't really need it to be that complicated. So Charles' Law in practical application. I'm going to skip down. Overall, I've got a better use for Charles' Law here in a little bit. So let's talk about this one for a minute. Nitrox is a term used to describe breathing gases made of oxygen, nitrogen mixes with the oxygen percentage higher than. Dallin?
Sorry, one second. I had a lot of noise in the background just for a second.
No worries.
Let me
good. See if I can make it a little bigger for you. Is that bigger? Nah, it looks about the same size, doesn't it? Is that better? Can you see it more easily?
Yeah. So if it's breathing in nitrogen and absorbing, let's see, nitrogen mixes with a oxygen percentage higher than.
it's any mixture higher than 20.
So if oxygen is 21%, wouldn't it be C 21%?
Yes. Now here's magic answer for the day as well. I know I use that term a lot. Overall, any gas mixture that contains oxygen and nitrogen is going to be a nitrox mix. It's a mixture of nitrogen and oxygen. What we generally consider to be nitrox, or a mixture of nitrogen and oxide, is going to be anything higher than 21%, or anything what we're accustomed to using for simplicity, right? But in truth, any mixture of oxygen and nitrogen combined without adding a third gas is going to be considered a blend of nitrox, truthfully. But for diving, we're going to keep it simple for you guys. Any blend of 21% or more. Don, how about this one? The percentage of oxygen needed in a gas mixture for a diver to maintain consciousness at sea level is what?
At sea level, that's going to be C, 16%.
That's exactly right. All right. So let's talk about Dalton's law and practical application. Here's what it looks like. Dalton's law is the basis for most nitrox calculations. Here's how we really figure out Dalton's law and what it really ends up being. So let's talk about first. Surface partial pressure is 21%, 79%, right? Feet seawater is 33 feet is 2 atmospheres. Does every jive with me so far? So if we have 2 atmospheres at 21%, we have a mixture of 42%. At 2 atmospheres, 33 feet seawater, right? At 3 atmospheres, so we multiply 3 times 0.21, that's 63% oxygen. That's 3 atmospheres, or 66 feet. On the other side of that, we have the nitrogen. And nitrogen is something we need to start considering what the partial pressure that we're dealing with in nitrogen. So at 2 atmospheres, the partial pressure of nitrogen is doubled to 158%. Now, a couple safety notes to be aware of. The first one is oxygen becomes toxic at 160%, or partial pressure 1.6. So the working load that we always want to make sure we're staying at for the safety factor is always going to be 1.4, or 140% partial pressure nitrogen or oxygen. Nitrogen becomes narcotic at 237%, and nitrogen becomes unsafe at 395%. So at that 395, nitrogen will equal 1 martini on an empty stomach at 100 feet and increase exponentially, not linearly, from thereafter. So I know in what you guys have been used to looking at as you figure out the partial pressures of things for your for nitrox is you've always all been looking at one side of it. I'm going to encourage you guys to take these 2 numbers down: 237, 395. That's 60 feet and 100 feet. Just so you guys got a quick, easy number on that. So as you guys are figuring out your dives, take a look at the partial pressure of the nitrogen you're breathing. Because in a lot of this is just because I could breathe 40% nitrox, do I really need to breathe 40% nitrox? If I'm doing a 50-foot dive, does it make sense to breathe 40% nitrox? Dwayne, what do you think?
Say that again. What was your question again? If
I'm diving 50 feet, does it really make sense for me to do a maximum blend of 40% nitrox?
I guess not.
Didn't think about that, did you? So overall, that's what we're trying to say is as we start getting those speed limit ideas of what works and what doesn't, understanding that nitrox becomes narcotic at 237%, and it becomes unsafe at 395. So we as divers, a lot of times we'll say, oh, I'm going out to do a reef. That's fantastic. The reef is at 45 feet. Go ahead and load me up with 40% nitrox. It just doesn't make sense. It just doesn't jive out. You really don't need to do 40% nitrox for a 45 or 50-foot reef dive. You can do a much lower blend and achieve the same results. You're still staying well below that 2.37% of nitrox or nitrogen. So as you guys start looking at it, I want you guys to start thinking about what's the other side of the coin. What does that look like to me? How is that going to affect me? Because as we go through these studies, we tend to look at only one side of it. we forget that there's two sides. There's two different gases we're dealing with. Now, Jolene, of the two gases we're breathing, air and oxygen, which one arguably is the more dangerous of the two for a human?
I'm going to say nitrox.
Nitrogen. Yeah, nitrogen, right? Why?
Let's open that up for discussion.
It's fine.
Because it comes out of solution when you
There you go.
you get the bends.
There you go. Exactly. Exactly. So that's the first and more deadly part of it. You're more likely to get DCS or the bends than you are to get oxygen toxicity, than you are to get just about anything else, nitrogen narcosis, right? But here's the second part of that is to think about is in dangers of nitrogen in the blend, what will happen first? Oxygen toxicity or nitrogen narcosis?
I think the nitrogen narcosis, right?
Absolutely. Absolutely. It takes quite a bit for oxygen to become toxic, right? And we'll go through that a little bit deeper in a little bit. But so think about that. We've been measuring the good gas in our blends as we start looking at nitrox. Why haven't we been measuring the bad one? I mean, we certainly, if we're doing those diet things, we're certainly measuring the amount of protein we consume in the course of the day, but aren't we measuring the amount of fat that we intake in the course of a day as well?
Yeah.
Yeah. So I want you guys to start, as you guys are going through and diving, I want you to start thinking about both sides of the equation, not just the easy, pretty picture of it. Because a lot of people, that's what they do. They just say, oh, okay, I'm doing a dive. Load me up with 40% oxygen or 40% nitrox. But you're doing I had one of my divers that got really excited and wanted to dive nitrox at the pool. He had Brett load him up with 38% nitrox for pool dives. And I was like, okay. And I talked to him about that. We did the math. And he says, yes, but I feel more energized after that. I'm like, yes, because that's called oxygen narcosis, right? There's a narcosis effect from oxygen that you can get, but it's certainly not harmful, but it's a placebo. It's not real, right? Overall.
Okay, so I have a question, maybe a dumb question.
No, it's not
So,
dumb question.
like when we are diving nitrox on the dive boat and they filled our tanks, we had to check the pressure and tell them what it was. And it was usually a 31 or 32. Is that the oxygen or the nitrogen?
That's the oxygen.
The oxygen level.
Okay.
Yeah.
That's not a dumb question at all, Jolene. It's I'm glad you asked, and please feel free to always feel safe enough to ask. There's no dumb questions. If you don't understand it, I need you to understand it. So please ask away. But yeah, we're measuring when we measure nitrox, we're always measuring the percentage of oxygen in the mix. The problem is very few of us ever take into account until you start getting into tech diving, and you start really getting into the hardcore idea of this, and you start narrowing those margins down. With recreational diving and nitrox, you've got a pretty wide margin of safety. The thing about it is the line is still in the middle there. As you get into technical diving, that safety margin starts shrinking dramatically. And so if you get the idea now, as you start moving towards larger dives, that wait a minute, there's two gases in there. Why am I not measuring both and getting an idea of that? It's to your advantage to start understanding it now. It makes it a lot easier as you go along. So, and again, just remember, we certainly be aware that oxygen does become toxic at 1.6. Is safe. Your safe working load is 1.4. But also keep in mind, nitrogen is, in my opinion, a far more deadly gas to deal with than oxygen. You're more likely to go into a narcotic effect of nitrogen than you are to go into oxygen toxicity. And I've got some cool slides later on in the deck about nitrogen narcosis as well as oxygen toxicity and the truth. So let's continue down that line. Dalton's law sounds more complicated than it is, but here's some interesting things for you. Dalton's law of practical application also helps us figure out what is the best mix for nitrox for us. And that's pretty handy. You can certainly use the chart, but I really would like you guys to understand the basic math behind it. So let's do an example. Guys, if you have paper, go ahead and pull it out. If a diver wishes to make a dive to 115 feet, what is the best mix for this dive? Here's the math. It's really easy. We're going to take the depth of 115 feet, and we're going to divide it simply by the solution we're in, which in this case is seawater, 33 feet seawater. If we divide 115 by 33 feet seawater, we come up with the atmospheric gauge pressure. Right, Dallin?
Yeah.
There you go. So 3.48 is the gauge pressure. Dallin, why am I adding the 1 back in?
Because of your atmospheric pressure and the partial pressure as you go down the 33 feet.
Absolutely. It's the surface tension.
Yes.
Absolutely. So that's what we're looking at is the surface tension.
Yeah. Divided by-
There we go. So we add that 1 back in. So now we got 4.48 actual atmospheric pressure at our 115 feet. Now we go back and we remember that 1.4 was the working load for the partial pressure of oxygen that we wanted to deal with. So all we need to do is simply take that 1.4 number, that's a constant, and divide that by our atmospheric pressure. And now we know that on a 115-foot dive, the best mix for us is 31%. Does that make sense? Are you tracking with me, Jolene?
Maybe not.
Okay.
I'm getting out my calculator. I have to visually see it. Sorry.
Perfect. Can you see it on the screen here?
Yeah.
So
we took the 115 divided by the 33. That equals
Why-
3.48.
Let's back up. Jolene, why 33? What's magical about that number?
Because that is the one atmospheric, like goes 33, 66, 99.
Exactly. That's the differentiation points of the pressure of the water we're diving. Easy
And then
enough.
you add the 1 for the surface atmosphere.
Uh-huh.
And then you get the 4.48. But then why did we divide it by something else?
So that, remember, we can only tolerate a specific partial pressure of oxygen.
Oh, the 1.4. Okay.
So you divide the 4.48.
No, look, that's 1.4 divided by 4.48. That gives you 31%. Okay. Do you understand
yeah.
that? Okay.
That's some funny stuff. Sorry,
So-
I sent a text. I thought I was sending a text to my wife to ask her for a fresh cup of water. I sent a text to Dawn. So Dawn sent me back a message saying, I know you can't have a cup of water. And I'm like, I didn't realize I was still texting Dawn. And I'm like, why can't I have a cup of water? What the hell? Thankfully, he told me this is Dawn.
Sorry, Ben. No can do.
No can do. Perfect. Okay, so let's go back to this. So we divide that out. We get our surface, or our gauge pressure. We add in the surface pressure, gives us our atmospheric pressure. We can only stand 1.4 partial pressure of oxygen. We want to stay at or below 1.4 partial pressure of oxygen. So that's the maximum we can do. So we simply divide that by our atmospheres, and it gives us a percentage of the oxygen that the maximum oxygen rate that we can use. Does that make sense, Jolene?
Yes, it does. So like on the dive boat, like they fill all your stuff, you don't have a choice. It was always either 31 or 32%. But very rarely did we ever even go to 100 feet.
Absolutely. Now, there's another half of this side of this equation. Dalton's law gives us a way to reverse engineer that. What happens if I get 32% in my tank? How deep can I go? So the good news is, I mean, we know from basic algebra that I can solve for X or I can solve for Y, right? It's all pretty basic stuff, right? If 1 + 2 = X, we know it's 3. If 1 + X = 3, we know X is 2, right? We're able to take the equation either direction. Same thing with this. So if we wanted to go the other direction, say, wait a minute, they gave me this blend, they gave me 40% nitrox. What does that work out to? So simple enough. A diver wants to know how deep he can dive with a mixture of 40% nitrox. So simple enough, I'm going to take that 1.4 divided by the percentage of nitrox that they've given me equals 3.5. All I simply need to do is take away the surface tension in this case, take the gauge pressure out. 2.5 is now my atmospheric, how deep I am. So I can take that 2.5 multiplied by my atmospheres, 33, and my maximum depth on 40% nitrox is 82.5 feet. So I can take it the other way. I could, so in your case, let's see. Let me move this up a little bit. All right. So you're saying on the boat, they gave you, let's see, so we'll take 1.4. We're going to divide that by, you said you got 31%, 0.31, right? Equals, who's got the answer for me?
Maybe you could do 1.4.
4.5 is exactly right. So simply enough, I had 31% nitrox. This is my nitrox. This is the partial pressure. This is my limiting factor. This is the speed limit for the freeway that I'm driving. So now I know that I can go to 4.5 atmospheres, but I also have to remember that I need to deal with not just total atmospheric pressure. I need to deal with gauge pressure. So I simply take that 4.5, subtract out my gauge pressure equals 3.5, right?
Right.
Easy enough. Now all I need to do is I'm at 3.5 atmospheres. I just need to convert that out to feet so I understand. So 3.5 times, or I'll use an X instead. Makes it times 33 feet equals
115.5.
That's exactly right. 115.5. Now, good news is for you guys, in your SSI app, there is a chart that you can check. So let's check it. So if we go to best mix and we say 31%, we know that 1.4, the deepest I can go is 116 feet. They round up. A half a foot among friends is not gonna change anything, right? If I decide to be brave and I want to do 1.6 where it becomes toxic, I can do 137 feet. But the good news is we can look at this. Our first equation where we said we're going to use nitrox at 40%. We can say, great, that's 82.5 feet. Let's check it. So 40%, 83 feet. Our second equation was 31% nitrox. Took this down. We said 115 feet, 31%, 116 feet. So we're right there. They're just rounding up.
So is that sorry about that. Is that chart on the app?
It is on the app. But here's the magic thing I have discovered about cell phones and diving is that I don't always have the best reception in the world. So and in some countries, I don't have the greatest cell phone reception either. So I don't know how your guys' Dwayne, Jolene, how your reception is when you go to Mexico on the boat, but I would guess that there are some times where it's not as fabulous as you'd prefer. And certainly that may be intentional as well. But you guys are probably cool enough to have satellite phones and all that cool stuff too. So, but overall, if you don't have your cell phone and you don't all you have is a paper and pencil, here's how you figure it out. Maximum operating depth is simply a matter of figuring out the partial pressure divided by the percentage of nitrox that I've measured in my cylinder. Once I've measured those two, I get that. I just need to take out the surface pressure so I can go back to gauge pressure. Measure gauge pressure against the depth, and it gives me a depth. The math is really not all that complicated. It's pretty easy to write down in your book as well, so you can take it with you. But you can do it both directions. So if I know I'm going on a dive, and I want to do, for example, Nikki and I's favorite dive is in Florida is called the Lady Luck. Really, really fun dive. So let's do the math on the Lady Luck for a minute. Let's see. I'm going to pull this up a little bit. Let's see. I'm going to take that down a little bit. Here we go. So we know that the depth of the Lady Luck is 125 feet to the deck. Okay. So that is our depth. All we need to do is take that depth of 125 and divide it by 33 feet seawater equals what?
125.
3.78, so 3.79.
Okay, 3.79. Perfect. Easy enough. Jolene, what do I need to do next? I've got gauge pressure.
Yeah.
You have to add one. No, or no, you take away one, right? Or no, you add one.
No, you got it. You add one, absolutely. Because that is the
That's that surface atmosphere. So that gives you 4.79.
okay. There we go. Easy enough. Next step. We know that the partial pressure of what I want to stay at is going to be 1.4. So now all I need to do is divide that 1.4 by 4.79 equals, who's got it for me?
.2922.
29%. So if I want to dive the deck of the Lady Luck, I'm going to run 29% nitrox. That's going to be best blend. Now, one of the cool things at good dive shops that you will go to is you'll be able to order up the blend that you want, and you'll usually get fairly close. Now, be aware, some of the blenders aren't as laser accurate as you might prefer. So in this case, we dove anywhere from 27 to 29% when we dove the Lady Luck. Some of our tanks were 27, and so we just simply adjusted. We adjusted our computers accordingly. But that's Dalton's law in practice. Why do I need to know Dalton? I don't. But knowing a little bit of algebra certainly doesn't hurt anything, does it?
No.
Does anybody need me to send these formulas or a copy of the slide?
No, we got screenshot.
Okay. No worries. It's so good. I'm happy. I just want to make sure. I'm happy to send the whole deck to you if you want. There's all kinds of cool stuff in the deck, but whatever
I'll
you
take that chart.
need.
Then I'll take that chart.
When I bought that one day.
Not a problem.
I never used it yet.
I will send. I'm just making a note.
I think it would be very safe if I had the chart.
Dalton's chart. I'm just making myself a note. There we go. Got it down. I'm going to send you that chart. I'll send you both best gas and best blend as well as mod. And the good news is most shops should, if they're worth their salt, should have a chart somewhere that you can look at. But I have been to plenty of shops that didn't have it as well. And Nikki will tell you that I prefer to do the math myself. I do it. I can't tell you. It's probably been 4 or 5 years since I've had to actually look at a chart for anything. She'll tell you that the only time I ever look at charts is with you guys. When we're on site, I just do the math. It's easier. I also make sure to keep on my computer. So those of us who use Shearwaters or DSXs, I also keep that handy on the partial pressure, the current partial pressure of my auction. I keep that up as one of the measuring factors on my computer, so I can see that. I have had the situation. We were doing a dive and kicking along. We'd been down for, I don't know, about an hour and 20 minutes or so. And I saw something that was interesting that I wanted to go after. It was some garden eels. They were really neat. I was very excited. Went out and then looked down at my computer and realized that I had hit a partial pressure of 1.7. And I was like, oh, yeah, I am too deep. So I'd headed out and got a little too deep. But it was nice to see the alarm for the 1.7 because while I was sort of watching my depth, I wasn't watching as closely as I should have. It was outside the planned parameters of the dive that I was currently doing. So certainly being aware of this and watching the partial pressures is to advantage. Now, interestingly enough, as we go through, let's talk about cylinders for a little bit. Anybody need to stop for a minute and get a drink or drink of water?
I'm good, thanks.
Okay. Well, I'm going to take just a quick break and I'll grab a glass of water then. Since I don't have a wife that will get me a glass of water.
You're absolutely right.
we go. All right, I've got a glass of water. Thank you. Thanks, Don, for getting that glass of water for me. I appreciate that. That was awesome. So one of the things that we can start looking at as we start figuring out, and this is back to physics as well, is how does pressure work in a tank? Different tanks hold different capacities, right? We have HP tanks, we have LP tanks. An easier way to get an idea of how our sac rate works is by understanding how many liters a tank currently has. There's two ways to look at this. You can certainly measure cubic feet by PSI, but the problem is there's going to be 3 steps of math that you're going to need to create an understanding of how many actual liters are in the tank that you're breathing. There's a simpler way to look at the pressure of a tank, and that's metric. I hate to say it, but I'm going to teach you guys a little bit of metric today. So overall, as we look at the cylinder pressure, it's helpful to understand if it's in bar and liters, it makes a simpler amount of math to work with. Now, simple enough, if we're diving an HP 80, that's 237 bar. An HP 100, 237 bar. Same pressure across the board. All we change is the amount of liters. So to figure out the amount of liters in a tank, there's one really easy calculation to do. It's called multiplication. All you need to do is simply multiply liters times bar, and it'll give you the exact amount of liters in a tank. Now, the problem is what you guys been doing so far in figuring out your sac rates is you've been figuring out based upon an incorrect form or an imperfect formula. You guys been doing a basis of calculations based upon at depth. You've been basing it upon a specific amount of time. So I've got, let's see, 3, 4, 5, 6 divers all together here. Who here can honestly say that they've gone down to 20 feet, stayed exactly at 20 feet for 20 minutes, and come up exactly at the 23 minute mark? Who's done that exact dive? Shut up, Aaron. Other than Aaron.
It was probably not quite perfectly accurate, but close.
Fair enough. So overall, none of us have done that. So the overall thing we have to understand is that we need to start with a perfect measurement. Dwayne, how easy is it for you to measure something in anybody, a reaction to anything, if you don't have the ability to have an accurate measurement of what's happening to start with? For example, if you're trying to administer XYZ drug, I don't know what drugs you're administering this week, but you don't know how much you're giving them each time, how easy is it to determine what the accurate reaction to that drug is?
Yeah, you can't have any idea at all.
Absolutely. So if you start with imperfect math and imperfect figures, you're going to get imperfect results, right? So what I want you guys to start doing is start thinking about, we're going to start with this, and we're going to back our way out of this. So here's how we figure out sac rate, and this is the best way to do it. What I want you guys to do the next time you guys get a cylinder and a regulator is I want you to take it home. I want you to sit down on your couch, put the regulator on. You don't have to put a BC on. That's just silly. But I want you to sit the regulator in the tank next to your chair. Find your favorite TV program. Mine is Big Bang. I know I say that a lot. I'm sure Jolene's is that whole English drama thing, the Downtown Abbey thing. That's Nikki's favorite. She loves that. Are you guys Downton Abbey fans?
She likes 2.5 Men, actually.
There you go. I like 2.5 Men. That's a good one. Right on. That fits right with Big Bang. So you sit down and you watch your 2.5 Men, and you put that regulator and put a mask on, and which just make sure when you do this for me, if you would, please take pictures because it's just fun. So sit down and you watch big 2.5 Men. You start off in that tank, you measure it out, and you say, I've got 3,000 PSI at the beginning. Easy enough so far? I breathe it for 20 minutes. At the end of 20 minutes, I have 2,000 PSI. How many PSI per minute am I using?
Like 20,000.
Well, so it's
By
1,000 times. Yeah. Divided by 20. Isn't it 1,000 divided by 20?
Exactly.
Bingo. I finally got one right.
Ding, ding, ding. Jolene, I'm doing this math just for you because I figured you'd like this. It's nice and easy. We have a propensity to make these things far more complicated than they really need to be. Here's the good news. This is how simple it is. It means that in, let's see, 20 minutes, I used 1,000 PSI, right? Simple enough. I just divided 20 by 1,000 and I came up with 50 PSI. Guess what? Your SAC rate for you is 50 PSI per minute. Do this 3 times an average. That's your baseline SAC rate. Pretty easy so far?
Yep.
Okay. Here's where it gets fun. This is the whole complicated portion of it. So if I know that my surface use rate is 50 PSI per minute, and I go to 33 feet seawater, how many PSI a minute is that going to now be equal to? Jolene?
You're going to double it?
Ding, 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 ding. How about if I go to, Dallin, if I go to, oh, sorry, too many sixes there. If I go to 66 feet seawater, that's going to be equal to what? It's a little tougher.
Is that like a quarter?
3 times.
Oh, okay. So 150.
Dallin, did I lose you?
Sorry, I'm still. Yeah, I'm here.
We wait 5 minutes.
If I'm at 66 feet seawater, how many PSI a minute am I going to go through?
So you're just gonna times it by the 3,
Uh-huh.
so it'd be 150.
Exactly right. Ding, ding, ding. And finally, Dawn, 99 feet.
Sorry, Ben. I'm trying to catch up here on some of this stuff. I got a pen now. Let's see. 3,000, 20 minutes. 2,000 PSI.
I use 50 PSI surface and I go to 99 feet. How many PSI a minute I'm going to use?
Let's see your average. 99, so let's see. That's 200, or is that 175? Yeah, that's
Exactly
200.
right. Yep. Multiply it by the atmospheric pressure.
Gotcha.
Right? Easy enough. Is that pretty basic, guys? Is Aaron, are you going to understand that? I know you're pretty dense sometimes.
Yeah, I'm getting it.
All right. So simple enough. As I'm planning my dive, I start off with the perfect amount. Dwayne, are my lungs the same size at 66 feet as they are at the surface?
No, they're a third as big.
Are you sure?
It's 66 feet. Yeah.
Are my lungs? How about my hand? If I wear an XL glove at the surface, what glove size do I wear at 99 feet?
Well, you wear the same glove, but
Absolutely.
But I thought it squished your lungs down by at 99 feet. They're a fourth the size.
My
Isn't that
shoes don't
true?
change size. My mask doesn't change size. Why would my lungs change size?
Well, just because of the
pressure.
pressure.
But
Yeah.
you're equalizing the pressure inside your body to the outside pressure, so they'd stay close to the same, probably a little bit less absorption rate, but I would say they're close to the same size.
They're the same size. The volume, the amount of volume is still the same. It's just the amount that's able to fill it within the container is changed because the pressure of the gas that I'm breathing is higher. So I'm able to fit more gas into the same space. I'm still
Right.
breathing. I still have a capacity of 2 liters. The average male is what, 2 liters, 2.1 liters, Dwayne?
Yeah.
Okay. So the liter volumetric size of my lungs is still the same. It's still going to be hold about 2 liters, but because the gas is twice as dense, or 3 times as dense, or 4 times as dense, it holds more. We've taken those marbles and we've turned them into BBs, right? And at the surface, the gas molecules are the size of marbles. At 66 feet, they're the size of BBs. So obviously, I could fit more BBs in the same size, but the container doesn't change.
Right.
There we go. So
if you're breathing compressed gas, then that offsets the change in volume, right?
exactly. You got it. Perfect. You're getting it exactly. So here's the thing: is if you use this formula overall and you get this idea, the volumetric of your lungs is not going to change. What's going to change is the gas and the gas density, right? So if I start off with a perfect measurement that my lungs are 2.1 liters, then I can figure out by the basis and the thickness and the density of the gas how much gas I'm going to need. Does that make sense?
Right.
Easy enough. So this is the way to start with a gas calculation of SAC rate. Now, my biggest disagreement with SSI is they want to have you figure out your SAC rate at 33 feet. But who can tell me what SAC stands for, Dallin?
Oh, I know this one. Can I say it?
Absolutely.
Surface air consumption.
So for me, this falls under the category. Dallin, what color was Custer's white horse?
White.
Exactly. So if we're figuring out the surface air consumption rate, wouldn't we want to do it at the surface? I'm just saying, I'm not a genius, but I'm going to go with one of the 3 words in the sentence we're talking about. So
But only the word.
that's my biggest complaint. And the funny thing is they changed their song when you start getting into tech, and they go more to this direction. But I wanted to introduce this to you guys now. Here's how we figure out SAC rate. Now, there's another component to this that we have to take into consideration. Dallin, do you go through more air running a sprint around the track at IF High School, or sitting on your couch enjoying a nice cold beverage?
Well, if I ran a lap around the track, I would say there, but I'm gonna, yeah. So definitely using more air running around the track.
Why?
Because your body's being more involved and exerted, and having to deliver more oxygen to accommodate for your exhale or physics. I guess I don't know. I think I'm just burying myself here.
No, you did good. You hit it. You hit it exactly. Effort.
Okay.
The amount of effort changes, right? And as we create more effort, our body needs to consume more oxygen. Or as we need to consume more oxygen, our heart pumps faster. As our heart pumps faster, we suck more air. It's pretty simple process, right? So effort. So are all dives created equally effort-wise, Jolene?
No.
Right on. I like it. That was some confidence right there. So
Yeah.
should we, in figuring out our SAC rate and how much gas we're going to need for a specific dive, should we take into account the effort of a dive?
Absolutely. Like we've done a current dive that we were going against.
Oh,
and
yeah,
I could not do very much.
exactly. So here's how we figure that out. The average Caribbean dive in warm water, if you're doing a straight drift where all you're doing is floating in a wetsuit, relax, is going to be 1.25 to 1.5 effort. A heavier current could be 2 to 2.5. A dry suit in cold water. But thin this down so you can see the whole page. A dry suit in cold water will be 3.5 to 4.5. Donnie, did you suck more air ice diving than you do at a Caribbean dive?
Yeah, quite a bit more actually.
Absolutely. So your body needed more oxygen. There's another side of this that I want to talk to you guys about as well, but let's just stay with this one. So simple enough. We all decided we're going to go. Dwayne has graciously invited us to all come to his boat this afternoon, and we're going to do a dive off of the coast of Mexico. Warm water. We're going to do a floating easy Pacific dive. It's going to be wonderful. We're going to see some rays, and we're just going to float along the reef and enjoy it. So We're going to say 1.5 is our effort. And we're going to do that dive to 66 feet. Our sac rate is 50 psi per minute. What is our new sac rate for this dive?
Is that a multiplier, the effort? So you're going to multiply?
It is. There's 2 multipliers there.
So the 1.5 times 66.
No. So first off, it's here's what it's going to look like. 1.5 effort. Let's see. Times my sac rate of 50 psi per minute equals 75 psi per minute, right? 66 feet seawater is how many atmospheres?
2.
No, there are 3 atmospheres.
3 atmospheres. So simply enough, 3 times my 75 psi per minute equals 225. So for that dive, we're going to go jump off of Dwayne and Jolene's boat. Is going to take, for that dive, we're going to need 225 psi per minute.
Does that all make sense? Yeah. Okay.
So we had to multiply by the time and by the depth. Or not the time, I'm sorry, the effort. I apologize. By the effort imposed. If this was a bigger dive, if you all decide to come ice diving with me, and we're going to do a 66 foot ice dive with it. So that's going to be we'll just put it as a 4 effort. And we know we're 50 psi per minute. We know that this suddenly changes to 200 psi per minute right there. We're doing 66 feet. We simply need to multiply 66 or the 33 atmospheres by the 200 psi per minute. Simple enough. For that ice dive to 66 feet, we're going to need 600 psi per minute. Now, this is a generalization, but it will get you within about 95% of where you need to be. Other factors are certainly contributing factors to how much air you will go through in a sac rate. Okay. One of those factors is how comfortable you are on the dive. It's one of the reasons that the more you dive, the less gas you use, because the more comfortable you get, right? Everybody remember their first time soloing in a stick shift car in downtown? Anybody?
Yes.
Yeah, that was a little stressful, right? Yeah, absolutely. Trying to get the stop sign, trying not to hit anybody, not trying to stall the damn car. Yeah, it's definitely, it's stressful. You go through more air. Same thing as a newbie diver. You go through more air because you're not as comfortable, right? So the more you become, the less gas as well. So you definitely need to make sure you take into account the mental stress of the dive as well. So why should I take into account, or how would I take that into account, Jolene?
I don't know how you put a number on your mental stress, but I think you have to be physically aware of it.
Sure, absolutely. And there's not a way to put a specific number on it. Absolutely not. But has anybody here done jumped into, say, a river with no visibility where they'd never been before, with a heavy current on a line where they felt that they weren't sure what was happening?
So never on a line, but we did go into a fire hole where you had to pretty much follow the instructor.
I love Firehole River. That is a definition of separating the big boy divers from the big people divers from the little people divers, right? It'll definitely put hair in your chest or take it off one. I'm not sure which, but definitely take that into account. So if I'm doing a new dive, I know it's going to be current. There's going to be some cavern, there's going to be whatever. I definitely want to make sure I take into account the mental stress that's going to happen with that as well. If I don't, I'm certainly doing myself injustice. Now, cave divers, for example, they do something different. Rather than having out their gas, they use something called the rule of thirds. So what the rule of thirds basically says is that I use one part of the gas out, one part of the gas back, one part of the gas reserve. If I start with 3,000 psi, I need to be back and on the shore at 1,000 psi, period. So I take into account the idea for additional redundancy and a little bit of extra safety factor as well. There's another part of this as well that breathing patterns definitely take into account as well. So Dwayne, what happens to your body? What does your brain kick in and start thinking when you start holding your breath?
Well,
It doesn't work right.
yeah.
Absolutely. Do you decrease the amount of oxygen consumption, or does it actually cause an increase on that?
I would think it would increase your oxygen consumption.
Absolutely. You deprive your body of the oxygen. It still needs the oxygen, but now all of a sudden it hasn't got it. So now it's got to make that up somehow. It has to deal with the deficit. So that's another piece of this as well. Now, if we go back and get the idea that I've got the basic math on this, does this math work on every cylinder? Dallin, what do you think?
It should, as long as you're checking everything the way you did, as far as checking your PSI before dive, and then recording your time and checking the PSI once you complete your dive.
Okay.
Unless there's an issue with the cylinder itself.
All right. Let's just check that, though. Let's see. Let me share my screen again. Present. Share screen. Please, no, don't share that to me again. Thank you. Entire screen. All right, Mr. Allen, we were looking at, sorry, I pushed the wrong button, sorry. We're currently looking at cylinder values. Now, these are all in metric, but if I have an HP 80 and an HP 100, which one holds more gas?
Wait, hold on. So it'd be your HP 100?
Absolutely. And which holds more gas, an HP 100 or an HP 133?
An HP 133.
Okay. So we're looking at this chart. Can you see the chart?
Yes.
Okay. So it goes from 80, 100, 120, 117, 133. The next line is the service pressure, 237 bar, which is 2,436 PSI. Okay. Is there a variation difference in the PSI in any of these tanks?
No.
Sorry, I'm trying to figure out where that is.
Second line.
Oh, gotcha.
HP 100.
So no.
Okay, good. So they all hold the same pressure, right?
Yes.
What's the next line tell us? The actual volume.
So the volume changes from tank to tank.
Absolutely. So 3,000, we're going to say 3,500 PSI for easy numbers, right? So 3,500 PSI at 10.5 or 10.2 liters is going to be less air than 3,500 PSI at 12.9 liters, correct?
Yes.
Okay. So I re-asked the question. Is the math that we just looked at able to be used on every cylinder?
No.
Why?
I'm still trying. Well, yeah, your volume and everything changes from cylinder to cylinder, but if you're doing I'm still confused because if you're doing your math the way that we did it to figure out your sac rate, then there shouldn't be a reason you couldn't figure. I don't.
You can. You can. Here's the catch. The rub is that if I go home and I do this math, 3,000 PSI for 20 minutes, and I divide out on an 80 cubic foot cylinder, and I suddenly switch to a 100 cubic foot cylinder or 117 or 108 or whatever,
changes.
I need to do the same math on every cylinder that I run. Would that be accurate?
Yes.
Okay. You would, absolutely. So you need to, or do you think there might be an easier way to do that?
Is there a chart?
I don't. I'm with her. Is there? Yeah, exactly.
There it is. So you can certainly do the math on it. The easiest way to do this is to first find out how big my cylinder is. Okay. So we're going to say we're using an 11-liter tank, an aluminum 80. Okay. So simple enough. We'll go down. I like being able to talk. Let's see. Mental stress. Let's get rid of it. Oh. I'm going to delete mental stress for a minute here. So if I've got an 11-liter tank and I know that I'm filled up to 200 bar times 200 bar,
Liters, which is the same as liters.
what the heck? What's going on here? Come on. So, give me 1 second here. Sorry, my computer's acting weird here. There we go. So, here's where it gets easy. So 11 liters. Sorry, my computer's doing something weird and acting funky. So I know that 11-liter tank at 200 bar now is how much? 11 times 200 equals 2,200 liters. Fair enough. Easy math so far.
Yep.
Okay.
Yeah.
If I have a 15-liter tank at 200 bar, it equals what?
3,000.
Exactly right. Good job. Somebody's good at math today. I like it. Perfect. All right. So simple enough. Here's an easy thing you can do is I can convert bar to PSI very quickly and easily. 0.0689. Okay. So 3,000 PSI sorry, my times.
What are you talking
206.7.
Yep. So my conversion is 0.0689. If you can remember that number, you can convert any tank to bar and you get this formula out. Now, if I went back to this, my initial formula and said, wait a minute, I'm going to start at 3,000 PSI. So 3,000 PSI is how many bar? $206? Say 207. We'll round up. Well, let's say we'll make it easy. 206 PSI of that, right? And if I go down to 2,000 PSI times 0.0689 is 137 bar. Okay. Now all I need to do is subtract 137 minus 206 equals 69 bar, right? 69 bar divided by 20 is now 3.45 liters per minute. Dwayne, do you measure anything in liters per minute where you're at?
When they're on the ventilator and stuff like that, yeah, you do.
Absolutely. Is that a pretty easy way to figure things out? Liters per minute?
Yeah, it's a lot easier.
Yeah. Metric is to your advantage. Once I figured this out, and I figured that I use 3.7 liters per minute. Now, Dallin, can I take that 3.7 liters per minute and use it on any tank?
Yes.
Yeah, absolutely. 7 days a week, twice on Sunday. So a little bit of metric and remembering one simple number, 0.0689, will allow you to convert any tank that you're going to use into bar, and then you can simply do the math. So now I can very simply say 689, I'm going to be diving. Where'd my, I hope I didn't close it. Oh, there it is. So easy enough. We're on a trip together, and I'm diving a 100-liter tank. It's filled up to 237 bar. 237 times 12.9 bar or 12.9 liters gives me 3,000 usable liters of air. Right? Now I know that I go through how much air per minute. I go through 3 liters a minute, right? I need to simply divide that out, and I can figure out how long I can get on a dive. Jolene, does that make sense to you?
Yeah, I think maybe I should use the chart that you had up there.
Sure. And I can certainly send that to you. My chart's probably a little complicated for most people. I'm happy to send it to you.
Is there an easier one?
Yes, I will work on making you a simpler chart. How about that?
Oh, that'd be lovely. Thank you.
I have, dang it, that's not where I wanted to go. Let's see. I'm sure you guys don't want to see all my daily reports. So here's the chart I use. So simple enough. I go through and figure out my actual depth. And so if we're going to do a 60-foot dive, barometric pressure, why would barometric pressure take into account for anything, Dallin? Why do you think that's important?
Does that increase your? Oh, sorry.
It does. It increases your theoretical depth. So understanding what your barometric pressure is changes your theoretical depth, changes the pressure of the water that you're going to be diving. Higher altitude, deeper depth. So understanding that. So we're just going to stick to sea level. If you're interested in understanding how diving at depth would change things, I do have a Science of Diving class that specifically for altitude. So it's just altitude diving. I think Dawn took it. Dawn, you took that class. What'd you think?
I did take it. It was short, it was sweet, and it taught me a lot. I didn't exactly think that reducing your atmospheric pressure was going to increase the effects of depth. But when you're acclimatized to a certain altitude, you're returning to that pressure, which means that you have to do deco a lot different. Like there's a lot to it.
Not more than most people think. But we'll stick simple for right now. So at 1 atmospheric pressure, our theoretical depth is still 60 feet. If we want to do a dive time of 30 minutes with 21% oxygen, sorry, I was doing some deco planning with something else, and I was using an 11-liter aluminum tank at 3,000 psi. My sac rate, honestly, is 9 liters per minute. I can tell you, in truth, that's a very, very good sac rate. My sac rate is actually 8, but I'd rather use 9. It gives me a little bit of safety margin. So simple enough. My work factor is 1.5, and we don't need to worry about the NOAA limits right now. So basically what this tells us is, well, pretty much everything. So as we go through this process, we can see that our partial pressure at that 60 feet is going to, oxygen is going to be 0.594. And then I think with that, or 0.594 is that we're within a limit. We're still below the 1.4. Our equivalent nitrogen depth, I like to figure that out, as 18.3 meters. So we're still within the partial pressure of safety for nitrogen. We're just getting to that point where it can become narcotic. At 60 feet, 3,000 psi equals 206.8 bar. The tank has 2,275 liters available in it. 2/3 of that gas for safety for me, because I use the rule of thirds on everything, is 1,500 liters, which means I will have 745 liters left over. That's how I figure out sac rate. But I wanted to expose you guys to this. This is definitely something that's going to be beyond you, but at this point, but I want you guys to get the idea of there's another way to look at sac rate. You can certainly do the easy math that I showed you, but be aware that if you switch from an 80 cubic foot tank to a 100 cubic foot tank, the sac rate that you just learned is not going to apply to that tank. The sac rate that I showed you initially only applies to the tank if you do it on an 80 cubic foot tank, it only applies to an 80 cubic foot tank. If you do it 100 cubic foot tank, that rate only applies to a 100 cubic foot tank. Now, Dwayne and Jolene, you guys both use Perdix, right?
Yes, we do.
Yeah.
Have you ever looked at your stack rate on the Perdix?
Yes.
Have you used different size tanks on with your Perdix?
Dwayne always uses a big ass tank, and I use a small ass tank, and we finish about the same time. Now let's do the math on that one, should we?
I think Dwayne just got owned. Wow. It's not often I see somebody get owned quite like that, Dwayne, but it's okay. It's all good. So, and there's certainly a reason for that as well. The average women have a much smaller lung capacity. They don't need as much oxygen, the smaller body mass, yada, yada, yada. Translation, Jolene whoops on Dwayne when it comes to sack rate.
Yeah. Whooping.
Easy enough. And Nikki has started beating me probably 3 out of 5 dives. She'll beat me in sack rate. 1 out of those 5 dives, we come out equal. One out of the 5 dives, I beat her. So, but it's taken a long time and a lot of practice on my part to keep that rate up. She's finally getting to that point where she beats me on a regular basis, and I'm okay with it. It is what it is. We still finish fairly close. We on the same tank. We after a 2.5 hour dive, we can usually finish with about 150 psi of each other, or roughly 20 to 30 liters of gas difference. So it's nice to see. But overall, I just want you guys to get the idea that not all tanks are created equal. If you guys were to switch out tanks, Dwayne, and you were to go from 80 cubic foot tank to 100 cubic foot tank and do the exact same dive, all of a sudden your sack rate would look much better. Does that make sense?
Yeah.
Perdix doesn't
So
have.
if you convert everything to bar and do it all in metrics, then the tank size doesn't matter. Is that what you're telling us too?
I'm not. I'm telling you, for figuring out the gas, yes, it doesn't matter. For measuring on your Perdix, it's still not able to take into account the size of the tank. It can only still look at the pressure differentiation.
Okay.
So it had the Perdix in your dive computer does not have a way to make a variation based upon on your tank.
Right.
Is there a computer that does that, Ben?
No, there is not currently. I am not currently aware of one that is accurate on that, and I have certainly looked. So there we go. Add Dawn back in. So it would be lovely if it did. I am currently working with the DSX from the shop. I like it. I think it's a great computer. It's the jury's still out if it's going to beat my Perdix. My bet is no, but Perdix is also being around for a lot longer. But either way, let's see. I dove the DSX, the Perdix, the Garmin. Let's see, the Aqualung 550, the Pro Plus 3, the Sunto Core, Eon Core, and Steel. So I've dove 7 separate computers that are top of the line, and the Sunto D5. And so there's 8 computers, and not one of them was able to accurately take into account the tank. So in gas planning, you have to do that before you put on your tank. You have to understand that I'm diving this tank. I have this much gas. I'm going to be able to do this much dive. Does that make sense?
But give it time, Dwayne. I'm sure someone will write the code and have it to where it can modify eventually.
It would be nice. I'm looking forward to that day, to be honest with you.
Well, I guess what would you do? Would you just say, what is it based off of? What is the sack rate on is it based off a 15 liter, a 12 liter?
That's unknown. I believe it's based on just on the pure change in pressure per minute. That's all it bases. It has no amount of data to say it's based on an 80, 90, 100, 200, whatever cubic foot tank. It has no basis for that at all. It only does its math based upon the pressure change only.
It would have to have some baseline, I guess.
No, just the pressure. So if you think about it, it says I go through 100 psi a minute. So my sack rate on this dive is 100 psi per minute.
Oh, it doesn't tell you liters per minute then.
No.
Okay. That's where I was confused. I was going to say, if it's converting something to liters per minute, it's got to have some liters to start with. But if it's just
it doesn't do liters per minute, it does bar per minute.
bar per minute. Okay.
Yeah, instead of liters.
That
It would be
makes
wonderful if it was able to calculate liters per minute, because then it'd have a volumetric ability to say this.
Well,
So
that's why I was confused why it didn't, if it was basing it off liters per minute as a sac rate.
sure, absolutely. So good news, Jolene. Here's your simple chart. I have it for you already.
Oh, nice. Yes, that would be helpful.
Yeah, I thought you might like that. There is a chart. There's a chart for everything, though. I
I'm just going
swear.
to laminate them and stick them in my dive bag.
So easy enough. Here's an AL aluminum 80, 11 liter capacity. Here's its cubic feet and current PSI. So you're able to do a very quick calculation utilizing this. And here's all your formula. I'll send this over to you. It'll make your life a little easier. But at least it'll give you a basic idea of how long am I going to get out of this tank. We talked about this, talked about this, talked about this. Understanding sec. Type example. All right. Jolene, are you ready to talk to us about buoyancy?
Okay, yes, I am ready for this. I've worked on this very hard. Okay, so Archimedes was a famous Greek mathematician. So famous, in fact, that the king of Greece had heard about him. Well, the king of Greece received a gift, a beautiful crown. But being greedy, he wanted to know if the crown was completely 100% gold, or if maybe he had been gypped by his gift giver, and part of it was silver. So the king, hearing about Archimedes and how famous he was with math, went to him and said, "Can you determine if my crown is 100% gold, or if there is some silver into it, and how much is each, if there is?" So not wanting to, say he couldn't do it, he said yes, and he thought about it quite a bit. Well, one day he was getting in the bathtub, and he started thinking about this. But he filled the bathtub with water, and as he sat in the tub, he realized that the water rose. And he started thinking about that. Anyway, he came to this conclusion that if he could find out the weight of the crown, if it was solid gold, and he could put it in the tub or a bucket of water, that he would be able to find out, oh dear, now I've lost my thought.
The displacement.
Yeah, the displacement, and find out if it was all gold. And if you could find the same measurement for the silver, do the same thing for the weight of the crown in silver, and put it in the same density of water, that he would be able to determine if the crown was all gold or if it had some silver in it. Anyway, the way he figured this out, the formula was the volume of the object times the density of the liquid minus the weight of the object. He was so excited when he figured this out that he got out of the tub and ran naked through the streets saying, "I figured it out. I figured it out." Anyway, the end of the story, it turns out that the crown was not all gold and the king had been given a cheap gift.
Bad news for somebody else. So there's the history of it. Now, how does that work in practical application?
That I think that we should open it up to discussion. But it is the buoyancy, like the uplift that raises you up. That is the buoyancy, is the force, the upward force that is lifting the object in the water.
Absolutely. So as an object is buoyed, is placed in a liquid, it'll be buoyed up by a force that is equal to, less than, or greater than the liquid it displaces.
Equal to.
Everybody want to agree with that?
Yes.
Dallin? I haven't picked on you for a minute.
Yes.
You agree that that's correct?
Yes.
Absolutely. The easiest way to remember that, to be honest with you, is going back to Newton's first law. For every action, there's an equal and opposite reaction. So as I push water down, it'll be buoyed by the same amount of force that it displaces. So now Remember, I asked you guys to remember a specific number for every foot of water, for every foot of depth in fresh water, pressure increases by, who's got it for me?
Just a minute. Fresh water is 0.432.
0.432 is exactly right. There are two numbers. How about seawater?
It is the 0.445.
Exactly. Those numbers come up a lot. Let's return to this. So if an object is denser than the liquid in which it is placed, it is negatively buoyant and will sink. If an object is less dense than the liquid which it's displaced, it will be positively buoyant and float. If an object is the same density of the fluid which is placed, it will be neutrally buoyant and will remain suspended at the depth to where it's placed. Dallin, why is that important?
Because when trying to practice perfect buoyancy, you want to be able to
Not sink.
yeah, exactly. Thank you.
Exactly. So what causes you to lift then?
So the fact that with you being weighing less than the water, then you're going to rise. But if you're going to weigh more than the water's pressure, then you're going to sink.
So sure, you're creating a density less than the water by adding air to your buoyancy compensator, correct?
Yes.
But if you don't have enough air, then your overall density is less than the water, so you sink, right?
Yes.
That's basically, Archimedes was our wonderful guy that figured out if you add air to your BC, you float. If you let air out of your BC, you sink. Now, unfortunately, for some people of us out there, we need a little more air than our BC than some, and there are some out there that need a lot less air than and need a lot more lead to get them down. So Archimedes basically gives us the idea of buoyancy, so that we understand that as we add a little air to our BC, that we will start to float, and we want to make sure that we keep that point, that we don't have to add too much air, because there is a limit to the amount of density. Reduced density that we can add. If we add too much lead to us, that our BC won't be able to compensate that, because we've added too much density. Now, tell you a story about this. 3 years ago, there was a dive accident at Lake McDonald in Glacier. Here's what happened. They were doing cold water dives. They had several instructors out there that were fairly inexperienced instructors. They were not certified to teach dry suit. They had a young lady who was diving a wetsuit, and if you have to walk through the snow to get in the dang water, you shouldn't be wearing a wetsuit. I'm just going to put that out there. You're a special individual that needs additional attention. But she was wearing a wetsuit because she didn't know any better. So her instructor decided that it would be a good idea to sell her one of her used dry suits. The problem is the instructor was very inexperienced and didn't understand the basics of Archimedes, or Boyle for that matter as well. So she decided not to sell her the hose so she could add inflation to her dry suit. Bad idea. The young lady was asked by somebody else, shouldn't you have an inflator for that? And the response from the young lady was, well, my instructor said it's probably going to be okay, so I'm going to go with that. Bad idea. We obviously are not understanding Archimedes or Boyle. They got out to the dive, and the instructor left them, and so it was two students by themselves, and they started to go down, and they couldn't get down, so they returned to shore. They started adding lead. Now, anybody that's worn a BC realizes there's always so much lead you can add to a BC. Well, they'd added all the lead they could to the ditchable weight pockets, so they decided to put lead in the pockets of the BC as well as the pockets of her dry suit. They added 40 additional, I need to stress that, additional pounds in pockets that zipped and closed. The average 8 to 10 liter BC has a lift capacity of about 30 pounds. I'm just going to put that out there for you. Okay. So they've got 40 pounds on her additional to get her down. on a BC that probably lifted 30. So they started to go down. At one point, she was at 80 feet and she was sinking faster and she was not able to create positive buoyancy. She could not add enough air to her BC to create lift, to reduce the density of what she was overcoming. Her buddy, who was another student, was trying to lift her. And in this process, in the 10 minutes trying to lift, he ended up going through the majority of his air and she'd gone through the majority of her air. He finally had to let go of her and swim to the surface. She continued to sink. And they found her body at about 135 feet. When they pulled her up, they were finally able to rescue her. She had died of squeeze. The dry suit, because of boil, had actually squeezed in enough that it caused her to actually suffocate. She died of squeeze. So Archimedes and boil came into law and caused this young lady to die. There wasn't enough lift, and she wasn't able to create enough neutral density or less density than the water around her because of that.
Well, if she had removed her weights, would she have had enough to get enough lift to get up?
No. And here's why. If she had, so say she had 10 pounds of ditchable weight in her BC that she could ditch. Now, she'd been able to take all the weight out. She probably could have, yes. That was incorrect. So if she just ditched to 10 pounds in her BC, she probably wouldn't have, because what happened is she got to 80 feet. We'll say 99 feet for even numbers. She was at 4 atmospheres, which means everything was compressed by a factor of
4.
4, exactly. So the air in her dry suit compressed by a factor of 4. The air in her body, in the neoprene, in everything was compressed by a factor of 4. Her lungs are still the same size, but everything's compressed in to a point where it's actually pressing air out because of the dry suit. So at that point, there's a phenomenon. They call it the magnetic depth. And what you'll see is as some divers get deeper, they feel almost like there's a magnetic hand pulling them deeper down. What it really is, it's a fact of going back to boil. As volume or as pressure increases, volume decreases. You become less buoyant. It takes more to create buoyancy the deeper you get. There's been multiple cases that the most dangerous place to dive in the world is a blue hole in Egypt, and they have multiple deaths. They've had more dive deaths there than anywhere else in the world. Simply for the fact that people get down to the 140-foot mark and they don't have enough buoyancy to be able to buoy them past that depth. They become heavier and denser because of the additional exertion of pressure around them. Everything becomes denser. So this is where Archimedes comes into play. We need to be aware that we need to make sure that as we start our dives, that we're as close to correct weighting as we possibly can be. The way we do that is just like we did with the other day with you, Jolene and Dwayne, is we've got you down to a very low tank, and then we got you to a point where you're neutral at a low tank. That way you weren't overweighted. So if you did get to the point and you started adding all the air you could to that BC, which is designed, at 8 to 10 liters to carry 30 pounds, if you're at lightly neutral at 33 feet, you're slightly negative at 99 feet, you still have plenty of buoyancy to be able to pull you up. Archimedes is going to work in your favor in that because you're able to create less density than the air around you. So, interesting story.
Yeah.
Sounds like a horrible story.
It is. It's terrifying, right? The outcome of that was the dive instructor, the shop, and Patty were all sued and lost. They about 4 months ago, there was a final. Patty settled out of court and changed some drastic policies as part of what they did. Nobody's seen the instructor since the accident, at least not publicly. She's hiding somewhere and it was Gold Divers in Montana, and they have since gone out of business. They were sued for like $5 or $6 million, and Patty was sued for like $10 million, and the instructor was sued, but nobody's. They're considering a criminal prosecution against the instructor. So scary stuff. All right. Dallin, the greatest expansion or compression per foot happens in which depth?
So when we talk about the 90 foot, so it would be the first 33 feet, the D.
Ding, ding, ding. Exactly right. Good job. All right. Which physical law states if temperature remains constant, the pressure and volume of any gas are inversely related? Don, what do you think?
If temperature is constant, that's gonna be boils, I believe.
That is Boyle. All right, Dwayne, your question of the day is the absolute pressure at a depth of 165 feet seawater is. I guess it'd probably be helpful if I didn't had the answer right there, wouldn't it?
Yeah, 6.
I had another class. Apparently, I was explaining the answer. Does everybody understand the answer? Why? Jolene, did you get that?
Yes, because you divide it by the
33.
the 33, and then your
And
atmosphere.
add 1 for atmosphere.
Yeah, your atmospheric pressure.
Ding, ding, ding.
For absolute atmosphere, right?
Exactly. All right. Dwayne, here's a softball for you. Breathing gas consumption
Increases as depth increases.
Right on. Dallin, your turn. Don't look. What is the surface air consumption rate? This is for you from the manual. It's actually pretty straightforward. But what is the surface air consumption rate of a diver with 3,000 PSI rated 80 cubic foot tank who uses 650 PSI in 10 minutes at a depth of 33 feet?
Hold on.
65.
Oh no, I lost you. Hold on. Sorry, I'm trying to use the calculator on my phone, and I'm also trying to use this on my phone.
No worries.
So 650.
I can make it larger if that makes it easier for you guys.
So 32.5.
How'd you come up with that?
So you take the 3,000 PSI rated at 80 cubic feet cylinder, and then you take your, 650 PSI that you used.
Mm-hmm.
I gotta remember how I did it.
So would you divide out the 650 by 10? Divide the 10 minutes?
Yeah, you take the 650 by 10 minutes, which gives you the 65.
Mm-hmm.
And then your 33 feet divided by the 65. And then you're
Or 50%. Because 33 feet is 50% pressure, right?
Yes.
There you go. That's what you're looking for. You're looking for half of that, half the pressure. So if it's 650, half of 650 is 32 and a half. Dawn, your question of the day is a diver and his or her or their equipment. Let's get all the pronouns in there correctly. Equipment weighs 175 and are neutrally buoyant in saltwater. To be neutrally buoyant in freshwater, diving with the same equipment, he or she will need to.
In freshwater, they'll have to remove weight because they're more buoyant in saltwater.
That's exactly right. By the way, guys, these may or may not be, I will neither confirm nor deny that these may or may not be test questions right from your test. All right, Dwayne, if 0.1 cubic feet of air is needed in your buoyancy compensator to maintain neutral buoyancy at 30 feet in the ocean, what will happen to your buoyancy if you ascend 10 feet without deflating? And why?
4.
You guys are muted.
Oh, sorry about that. 4, your positive buoyancy will increase. And that's
why?
because as you go up, your BC will expand and you'll be more buoyant.
Absolutely. What law do we have to thank for that one?
Boyle's law.
Boyle's law is exactly right. All right, Don. At an altitude of 16,000 feet, the atmospheric pressure is approximately.
Well, I've seen this one before, but it's 1/2 of what it would be at sea level, so 0.5 ATA.
Exactly. Good job. All right, Dallin. Let's see how you do. How much breathing gas does an 80 cubic foot, 3,000 psi cylinder contain if the fill pressure is 2,200 psi and the temperature remains constant?
Oh, shit.
Let's see. That one I don't remember how to get. Let's see, 3,000.
So the 3,000 times.
So
So can we review that one? I can't remember how to do this equation for this one.
There's the easiest way to do that is simply take the 2,200 divided by the 3,000.
Okay.
We'll give you a percentage. Okay. So 2,200 divided by 3,000 gives us 73%. Actually, 73.33333%, but we'll say 73.33%, right?
Yeah.
But simple enough. All I need to do now is take that and multiply that times 80 cubic feet. So 73% of 80 cubic feet is 58.91. Or 58, I'm sorry, 58.66. I'm sorry. Apparently brain aneurysm today. So just simply take the 73.73 times 80. Equals, got to find the equal sign for sure. 53 or 58.
that's 0.73.
Yes.
Times
Sorry.
8. Yeah.
Thank you, Dwayne. You're exactly right. Or what I could have done, what I should have done, and what I was thinking is what
Percent. Yeah.
exactly. Sorry about that. I had it correct above. I just didn't carry that across. So 73% multiplied by 80 cubic feet is 58.66.
Okay.
All right. If the volume of gas is kept constant, what varies directly with temperature? I'll give you another one, Dallin. What do you think?
That one's pressure.
Pressure is right. Let's see. All right. The partial pressure law, Dalton, requires the sum of the partial pressure to always be equal to which? Don, what do you think?
That's going to be the absolute.
Absolute pressure is exactly right. All right. Assuming a maximum partial pressure limitation of 1.4 ATA, the mod for the maximum operating depth for 40% nitrox mixture in the ocean is? Jolene, you want to take that?
Yeah, 82.5.
Did you see
Thank
the
you.
answer?
Well, Dwayne had it here too on his little chart. You should give Don the harder ones. We need to be a little more selective in Dwayne and Dawn. You're giving them some, rather easy ones that Dallin and I could field,
Fair enough. Fair enough. All righty. If you guys wouldn't mind, we've got about 20 more minutes left in our class time. I'm going to move us over to a little bit of and give Dallin a chance to talk to us about DCS because I thought I heard that you were ready to be DCS presentation tonight. Are you ready?
Well, I was focusing on tomorrow, but yeah, I can swing it tonight.
We can do tomorrow. I don't care. I thought I heard you say you were ready tonight, but if I was wrong, that's fine. I don't care.
No, I totally forgot about class tonight.
Well, let's do it tomorrow, and we'll continue on the slide. I just want to make sure I was being respectful of your time. If you prepared, I wanted to make sure you got that taken care of.
Okay.
All right, guys, that was the hard physics portion. We've got some deco theory to go through, but we've covered a lot of deco theory already. I like to cover deco theory twice through this class. Now, let's talk about energy and underwater light environment and underwater environment. So as we go through this, we're going to talk about light and how it refraction, diffusion, turbidity, absorption. We're also going to talk about sound and how heat works, conductive, convection, and radiation. So objects do not appear the same underwater as they do on land. So there are four major factors to this. And the first one's refraction. And easy enough. I don't know if you guys can see the chart, but refraction, basically the light in the air travels 1.3 times faster in the water. And this changes its speed and causes the light rays to bend as the light speeds up when it enters the diver's mass. This gives the idea of a factor increase of 33% in waters. So everything underwater will look closer and look bigger. Anybody ever seen a fish that they swear? Let's see. I'm going to go back over so you guys can see me. Anybody ever dove and saw a fish they swear was this big? And then you did whatever and got up next to it and turned out it was only this big? That happens to me all the time at Ryrie. I'll be diving and I'll see these huge, what I assume to be huge crawdads. And I'll get them and I'll capture them. I'll put them in my bag and I'll get them to the surface. And they're literally 2/3 the size of what I thought they were. That's because as we look, and this is every man's dream, that where we're going, everything is closer and bigger. I swear my fish was this big. It really was. Yeah. Yeah, we've all had that guy that said it was this big, right? And really it was this big. Just kidding. That's one of the reasons, to be honest with you, the other day when I was diving with the sturgeon, that I purposely went over and I laid down next to one so I could use my body as a reference point. Because I tell you, when I saw him, I thought for sure he looked like he was 7 or 8 feet, maybe 9 feet. That's why I laid next to him so I could say, okay, he's about 6.5 feet because I can see where his tail is, I can see where his head is, and I know how tall I am. But I promise you, as you look at them, their tails look this freaking big. It's huge. Let's see. I thought I saw Aaron on here, but because Aaron's done that same thing. So be aware that because of refraction, the bending of light through the mask, everything is going to look closer and bigger. The next thing we need to worry about or deal with as we're dealing through this process is something called diffusion. Now, diffusion is when the light enters the water, the rays are broken up and scattered. The main effect of diffusion is less ambient light as we go deeper. Okay, so simple enough. It's diffused out. If you put a screen over your window, that diffuses the light or blocks the light, right? And both things happen in water. But we're diffusing the light so that we're not able to have as much light as we go deeper. It's one of the reasons. Anybody done a really nice 130-foot dive and noticed that it wasn't quite as bright as it was at the surface? Absolutely. It's diffusion. The other thing we deal with in diffusion and where lights are blocked is going to be turbidity. I think we've all dealt with turbidity. I think we all have a pretty good understand that crap in the water blocks the light, blocks your vision, and makes things tougher to see, right? So I don't know that we need to spend a tremendous amount of time on turbidity. Absorption is the next thing, though. As we go deeper, colors change. The visible light spectrum and gradients will start to decrease. Anybody remember studying Roy G. Biv in high school,
No.
elementary school, middle school, whatever? So R for red, O for orange, Y for yellow, G for green. As you go deeper, what ends up happening is the absorption of the wavelengths of light are absorbed by the water. So as you get to about 15 feet, you start losing your reds. You get to about 20, 25 feet, you start losing your oranges. 30 feet, 35 feet, 40 feet, you lose your yellows, and so on and so on. I've got a really great photo. Let's see. I think I actually have. Yeah, I do. I don't know where it's at on my computer, or I would get it out. Everybody see my photo? Can you guys see that? Here.
Yes.
Okay, so the thing right here, let's see, right there, that blue thing, that's my light. Anybody know what color my light is on the surface?
You're frozen. We can't see anything.
I'm frozen.
Yeah, our video kind of died some reason.
Interesting. Let's take a look here.
I can see everybody else.
Huh. You can't see me.
Well, your screen froze on us. I don't know why.
I can see you.
Well, that's all that matters then.
Can you see me now?
No, now you're totally black.
Yeah, that made it worse.
That made it worse. Better or worse? Better or worse? There we go. How about that?
No,
That's
it's
okay.
just a black screen.
Well, I apologize. Well, I'll just talk to you. We've got a few more minutes here. So the photo I was showing you is at a dive at about 70 feet where I'm chasing a turtle and I've got a bright blue light on my wrist. The problem is that light is actually bright pink. It's hot pink at the surface. But because of absorption and the wavelengths and the color changes, I lost all the color in my light. It is no longer blue. It is actually it's not no longer pink. It looks blue. So I'm gonna go back and share my screen. So it happens. That's one of the reasons we want to make sure we carry an additional light when we dive, because that way we can replace the wavelength of light where we dive. There we go. Can everybody see my screen?
Yes.
Mm-hmm.
Yes.
There we go.
Yeah, that's good.
All right. So the reason that happens is because red is the fastest of all the lights. And as we all know, that if you go fast, you don't go far, right? If you have a hardcore sprinter, he can sprint 100 yards, but that's about it. So red is our fastest of lights. Then our orange is slower, followed by our yellow, our green, our blues, and so on until we finally get to the slowest of lights. And slower the light wavelength, the deeper it's able to get. Turbidity we talked about. I think we've got a pretty good understanding. So sound. Because water is a lot denser, sound travels approximately 4 times faster in the water than the air. The denser the median, the faster the sound travels. So sound travels a bit faster in salt water than in fresh water. The faster the rate of the sound travels has effects on the diver. The brain uses time differentiation between the ears to determine the sound direction. Sound is delayed about a quarter that of the land. So sound is perceived as being all around the diver. Anybody ever dove where there's boats?
Yes.
You hear that motor? How easy was it to figure out how to get the jar of pickles open? Sorry. How easy was it to tell which direction the boat was coming from? Come on, Muscles, get the damn pickle jar open.
Yeah, you kind of have to look up and see if you can see the turbulence in the water.
Absolutely. For Donnie, I'll go ahead and maximize that out so nobody else has to watch you but me trying to open the chart. Being very Air Force there, buddy. So because the water is so much denser, we're not able to get that idea where the sound is coming from. It's definitely a very tough thing. But the cool thing is we hear everything. We know there's a boat around us. We know to be careful, but we don't know exactly where to be careful. So be aware that sound travels 4 times faster underwater. Now, some of the primary causes of sound underwater: rain. I've dove during the rain. It's definitely interesting. You hear that constant under. Storms. I don't dive during storms, so I haven't heard that. Cracking of ice. I'm hoping never to hear that sound. That is while diving. I've heard that plenty of times walking across the ice, and that's definitely a disconcerting sound as you're walking across. I'm okay without that. Marine life. I don't know if anybody's done this before. I had this really great dive that it's one of the ones that stands out in my mind. We did a scooter dive off the coast of Maui. So we're diving along. We did the scooters out to this little reef, and we put our scooters down, and we came up on the reef, and we went ahead and relaxed and held our breath. I know, don't ever hold your breath during diving, but we did for this, and there was a reason. Because the coolest thing happened. As we held our breath and relaxed and stopped moving, you could hear the fish talking. And they made all these great sounds. About a month or 2 months ago, Nikki and I were diving in Hawaii, and we were going down this decline, and we were about 75, 80 feet, somewhere around there. We left our GoPro to videotape something, but as we were leaving, we could hear the whales out in the water, it was a very surrealistic sound. It sounded exactly like a Jacques Cousteau movie. It was awesome. So sound travels very well underwater. And if you listen, you will definitely hear the marine life doing things. It's definitely neat. If you're in the river, you can hear the current. Definitely something interesting. You can hear the surface waves. I'm hoping not to hear an earthquake. I'm okay without that. I've never felt an earthquake, never been in an earthquake. I'm pretty okay without an earthquake. So I don't know what that sounds like, and I'm okay with that. Hydrovents. We dive Yellowstone, and there's a place called Mary Bay that has a lot of hydrothermic activity, and you can definitely hear them in the water. We've all heard boats, sonar. There's a couple of us that dive the Mark II Garmin. It uses sonar in its pods, and it's interesting because it's using sonar to communicate. You can hear it, and it makes a sonar ping about every 2 to 4 minutes. I think you guys heard that one time. Somebody I was diving and teaching with. Yeah, was it you guys?
Oh, no, I was going to say, so we were in Roatan, and we did have an earthquake while we were under the water.
Oh, my goodness.
We did not know it, but the guide, when we got to the top, and the boat captain said, "Hey, did you guys feel that? Did you hear it?" And the guide said he did. None of us did.
Okay. Wow. That would be a stressful situation. I just hear an earthquake or feel an earthquake in the water. That's for sure. I'm pretty okay without that. All right. Now, heat. So one of the things we realized diving around here, heat is definitely, and heat loss during water in the water is definitely of a big concern. But Jolene, can you get hypothermia diving in Mexico?
Absolutely.
Absolutely. How about the Mediterranean? You're diving 91 degree to 89 degree water. Can you get hypothermia?
Yes.
Absolutely. With enough time, you can certainly happen. Heat travel is exchanged 25 times faster in the water than in air. So cold water increases the rate of heat loss dramatically. So as we dive, we want to make sure that we're taking that into consideration and adding an insulating factor. Now, one of the things most people don't realize is hypothermia and cold has a cumulative effect. Now, let's think about that for a minute. If I'm doing 3 days for 5 straight days, day 1, I get in the water feels warm. I get in the water day 5, the water will feel cold. It has a cumulative effect. It takes time for your body to recoup and to come back after being cold, after you're chilling it down. And even if you're diving, I love diving Florida in November. It's 81 degree water. It's wonderful. But I always dive a wetsuit to make sure I can serve as much and add as much insulation as I possibly can. Now, one of the considerations that a lot of people don't take into thought process is you go out and do these 3-a-day dives, or you go out to wherever you're in Costa Rica and you're doing some nice tech diving, doing a nice big 150 for an hour and a half. You got a nice 45 minutes worth of deco on that. So you're 2 hours and 30 minutes, 2 hours and 45 minutes in the water. You come back up to the boat. You go back to the hotel. Should you take a hot shower or hop in the hot tub? Good idea or bad idea?
The answer is no, but I can't remember why.
Dwayne, you want to tell her?
Why shouldn't you get in the hot tub?
Yep.
I think you should get in the hot tub.
Honey, get you a bikini, baby. Yeah, no. So if you get cold, what happens to your veins?
They restrict. They constrict.
Vasoconstriction, right? Well, wouldn't the opposite happen if you get warm?
Yeah, they dilate.
Yeah, vasodilation, right? So here's the thing is if you have built up residual nitrogen after a dive and you hop in the hot tub or take a hot shower afterwards, what's going to happen to the nitrogen that is in your fast and slow tissue?
It's going to come out too fast.
Exactly. Give yourself time and for that residual nitrogen to equalize and come out of your system before you decide to hop in the hot tub. Now, one of the things that we get into when we start getting into the bigger dives, every time I do a dive that I have to have a decompression obligation on, I do an additional safety stop. Okay, it's encouraged that tech divers do additional safety stops. So if I have a 30-minute decompression obligation, I come up to my 20 feet and then I come up to 10 feet. I do another 4 minutes, 5 minutes of decompression obligation of safety stop, right? When I get to the surface of the water, I encourage you guys, rather than just jump out of the water after any dive, give yourself 5 or 10 minutes in the water to do a body decompression. Allow your body to have a little bit of pressure on it just to allow some of that residual nitrogen to come out as well. What happens to your respiration rate when you're climbing out of the water with a 40-pound tank on your back and 10 pounds of lead, Jolene?
Well, it goes up. You're using a lot more energy.
Absolutely. Using a ton more energy, you're pushing a lot of pressure on your joints. What do you think that does to the residual nitrogen as you're coming out of the water?
Well, it bubbles out faster.
Absolutely. So you give yourself a chance to get the bend. So my encouragement to you guys is learn to do nothing. These dives, and when you go diving, take your time. Nothing should be hurried. Take a little extra time at your safety stop. Make sure you're wearing proper something to keep you warm, proper insulation, a 3-mil wetsuit, a 5-mil wetsuit, whatever appropriate that keeps you warm. Make sure you take into account that nitrogen's coming out of your system at a speed that you want to make sure it's coming out at the correct speed. Take a little time, extra time in the water, and do a body decompression for 5 or 10 minutes. It's to your advantage. So as we get through this process and understand that we need to insulate up, there's different thought processes on this: wetsuit, dry suits, exposure suits, and care and maintenance. So we start off with, if you're in extra Caribbean, you can certainly start with this, and it's really warm, 84-degree water. You can certainly start with a shorty. Generally, it's encouraged that the water temperature be between 75 and 85. If it's at that temperature, you should be at least wearing a shorty. 70 to 80 degrees, you should move to a 3-mil wetsuit. And I can tell you from personal experience and just how I like it, I'm a real princess when it comes to getting cold. I do not like being cold. I know Dawn doesn't like it either, and neither does Nikki. So we generally are a little more conservative on this. So when, for example, Hawaii, where the water was 75, 76 degrees all week, we dove 5-mil. So, and I see that it says on the chart here that you should dive a 5-mil between 60 and 70. For me, 60 to 70 degrees is a 7-mil. And I can tell you anything colder than that is a semi-dry. So the process is obviously 5-mil, 7-mil, and what we're looking at here is a semi-dry. So Dallin, what's the difference between a semi-dry and a wetsuit?
The buoyancy factor, as far as one being shorties, the 3-mil shorty, just no sleeves, whatever. So you're going to be less. You're going to be, sorry.
Yeah, right.
Sure, going to be less buoyant. Yeah, that's absolutely one part of it. So the real difference between a semi-dry and a wetsuit is the amount of flush. So the way a wetsuit works is it allows a certain amount of water in and a certain amount of water out. The insulating water that comes into the wetsuit is allowed to be heated up by your body and becomes a thermal layer around you. Now, a wetsuit will allow more water to flush through than a semi-dry. A semi-dry generally has seals around the neck, the wrists, and the ankles to reduce the amount of flush. My personal experience I dive a bare semi-dry that I like quite a bit. It usually takes 4 to 5 minutes for me to get wet, where I start feeling the water start to trickle in. It's not a dry suit. I definitely do get wet, but it takes 4 or 5 minutes. And when the water comes in, it takes a long time to get out. Pro tip for you, if you're used to peeing in your wetsuit, don't do it in a semi-dry. Just saying. It takes a long time to flush that pee out and get rid of it. Remember, there's 2 types of divers, those who pee in their wetsuits and those who lie about it. So I'm just saying, it's a good idea not to pee in a semi-dry.
Lane does not pee in his wetsuit.
Who does not?
Lane
Hackey.
does not pee in his wetsuit.
I'm going to refer back to my previous statement of there's 2 types of divers, those who pee in their wetsuits and those who lie about it.
I can vouch. I know he's not telling. I know he's not lying.
That is a tough day to be. That's for sure. I'm just kidding. I'm sure if he says he does it, I'm sure he doesn't. But that's the old adage. So, but that's the difference between a semi-dry and a wetsuit is the amount of flush. You get a lot less flush through a semi-dry. The painful part about it is if you do have to urinate in your semi-dry, you have to flush that out while you're in the water. All you're doing is sit at the surface. You're letting a whole bunch of cold water in, and that's just not fun. And you've just defeated the whole purpose. The next step up the chain is a dry suit. Dallin, do you have a good understanding of what a dry suit is?
Yes.
Okay. So the way a dry suit basically works is it has an air layer between you and the water between you. You wear thermal undergarments that are generally in fleece nature, and it's not the fleece garments. The fleece garments underneath retain the heat, but it's the barrier of air between you and the water that really keeps you warm. Okay. The nice thing is you can take that up to the next level. You can get a semi-dry hood, and you can add dry gloves as well. So I dive dry gloves. So does Dawn, where we put a fleece line glove on, and then we put a rubber glove over top of that, and it seals in. So literally the only thing that ever gets wet is our hair a little bit. And when I'm diving dry for ice, I wear a full face mask. So my head gets a little wet through my semi-dry hood, but I stay pretty warm. So overall, the colder you get, the colder it is, the more thermal protection you're going to want to be. It's definitely important as well to make sure that you're staying warm for safety as well. Because the problem is as you get cold, Don, what happens when you get cold to your blood flow?
Are you talking about shunting, or are you talking about just the decrease in your body's ability to push blood out?
Why would you have a decreased amount of ability?
So as you get cold, your body tries to retain heat to the core, so it shunts things or blood away from the surface tissues.
Mm-hmm.
Let's see. I'm not sure exactly what you're leading on to here.
How about vasoconstriction? Is that a thing?
Yes.
Why?
Again, your body's trying to retain that heat. The smaller the blood vessels, the less heat is transferred out away from your body.
Yep. And as every guy in gym class will tell you, as things get colder, things shrink. I thought you'd like that one. So as you get colder, you're going to get vasoconstriction just because as things get colder, things shrink. So shunting and vasoconstriction are 2 things. So if you have a reduced blood flow, how does that affect the amount of nitrogen you're able to off gas?
You can't get as much out.
Exactly. Now, there's a second part of that we don't talk about nearly enough, I don't think at least. The second part of that is going to be Henry's Law. And I alluded to it earlier in our conversation, but in Henry's Law, it talks about how absorption of a gas into a liquid happens. It happens by Agitation is the first one, the heart pumping, right? Pushing it through. The second one it has to deal with is the temperature of the liquid. The colder the temperature of the liquid that is used to absorb the gas, the faster it absorbs. It's more dense. If it absorbs faster, it's absorbed faster into the tissues as well. So there's several factors that we need to be aware of. We are on gassing a lot more nitrogen because vasoconstriction, because as we get colder, heart rate increases because of shunting, and because of Henry's law saying that gas will absorb more quickly into a cold liquid than it will into a warm liquid. So it's something to be aware of. As you get cold, slow down your ascent rate. Take more time on your safety stop. It's to your advantage. When we are diving ice, Don will tell you that my suggested safety ascension rate is 20 feet per minute or less. Take your time. All diving, you should take your time anyway, but definitely make sure you take your time when you get cold, even more so. All right, Dallin, this one's for you. Sound travels differently in water. The major difference is that it travels
approximately 4 times slower.
Ding, ding, ding. Good job. Yay. Good job, Dallin.
Times faster.
All right. Objects do not appear the same in underwater environment as they do on land. Some major factors that influence this difference in appearance are...
Is it still me?
Yep.
Oh, refraction, absorption, diffusion, and turbidity. And yeah.
You got it.
4.
Good job. All right. I'm done picking on you for a minute. Notice I said for a minute. I just want to qualify that. Jolene, our perception of light as it travels from the water through the glass of the mask and into the air pocket in front of our eyes, this gives a magnification factor of 33%. So next time Dwayne says, here, let me just switch over to me. Next time he says it was this big, we know what that means, don't we?
Mhm. Absolutely.
You're good sports on that. All righty. We've already done the patent formula overlay. Who is good calling it for tonight and picking up with Dive Malleys tomorrow? Because that actually catches us up where we're ready to go into DCS.
Yeah, we can do that.
Awesome. All right. Well, tonight we covered quite a bit. We actually covered a little more deco theory than you guys realized. We covered the how to use Dalton's law in practical application. We also talked a lot about sac rate and the use of gases through our system, as well as the differences in how sac rate actually works. Plus, does the sac rate calculation that we find in the book work on all cylinders? The answer to that, of course, is what, Dallin?
No.
No, it doesn't. So we have to realize the size of the tank. So we talked about that in depth, and I really want to get you guys the idea that just because you figure out a sac rate on an 80 cubic foot tank doesn't mean you necessarily have the sac rate for a 100 cubic foot tank. Either A, you do a sac rate calculation on every tank you're going to dive, or B, you remember a simple math of how to calculate PSI over to bar, figure out the liters, and know what your sac rate consumption is in liters. It makes life a lot easier, and you're able to do much more accurate gas planning for your dives. Now, good news is for you guys, for any of you that are interested in doing deep dive or deco diving or deco procedures or solo diving, let's see, I'm trying to think if there's any other classes, or just coming out diving in Ryrie in general with me. As a general thumb, I bring a notebook, a pen, and let you use your calculator. I hand you your tank and ask you to figure out how long our dive is going to be. I like to pass that off and make everybody figure out how many liters are their tank, their basic sac rate, and how long our dive is going to be, and do a little dive planning that way. It's a pain in the ass, but it works, and it gives you a better understanding. So just heads up, I would love for you guys to come diving with me. Do not be surprised if I make you do some math for our dive, because I want you to be safe and I want you to understand. So we talked about that in depth, the different sizes of tanks as well. We went through how the light travels, how sound travels in water. We talked a little bit about hypothermia as well. And I think that was about it. Are there any questions that we might have?
Not on that, but 8 o'clock tomorrow night, correct?
I believe so. Let's just pull up my calendar. Take me just a second here. Let's see. I believe that is correct, but let's take a look here. Dun. Yes, ma'am. 8 o'clock tomorrow night is what I've got us down for. You are good to go for 8 o'clock tomorrow night. Any other questions?
So with it being 8 o'clock tomorrow night, what time are we going to?
Probably 9 or 10.
Okay.
If you guys are drooping on me and having a hard time, I'll cut it at 9. If you guys are good for till 10, I'm good. I'm good till 10 too. So
yeah, I just have pool tomorrow with Brett, so I have 11:30 to about 6 in the pool.
Okay.
Or class and pool.
Not a worry.
So hopefully I have enough energy. I guess there's Red Bull for that.
There is Red Bull for that. And like I said, if you guys are drooping and you want to call it a 9, we can call it a 9. We're doing good on pace. For sure. We've gotten pretty far in. How is everybody doing on their homework?
Good.
Yeah.
We're through the book.
Yeah, we've done it.
You done all the book? Excellent. Jolene and Dwayne are good on the book. Dallin, how are you doing on the book?
I'm about halfway, and I started into the next section, so I'm almost done.
Cool. Don, how are you doing on the book?
I'm somewhat through it.
Cool. Gotcha. If you guys could get a little farther in your book, it'd be awesome if you guys all got all the way through it. But I do have a final test that I give you. It is oral. Just a kind of a heads up. I like to do an oral exam so I have a good idea where you're at. But your final passing test for the book work is actually online and in the book. So make sure you do that all, answer all the questions, look at all the pages, and make sure if you do it on your phone that you sync it to the Magic Cloud. So that'll be that portion. And then for I will do an oral test for you. And you have to sign off on the paperwork. The instructor has to sign off on you as well. And then you have to pop in the shop and give me some signatures in the shop. So there's 3 parts of the paperwork. One of them's on your side. One of them's on my side that I have to agree that you passed. And the last one is you just have to sign the paperwork. Dwayne, you're not used to signing paperwork at all, are you?
No, never.
Nothing to sign. Nothing to sign. I heard a statistic that there's I can't remember how many deaths it was, but there's a attributable number of deaths every year due to poor doctor signatures or poor handwriting by doctors. So a little on the scary side.
Hopefully not mine.
Hopefully not yours.
Yeah, actually.
I can tell you that I have a stamp for your paperwork, so I don't actually sign your stuff. I do sign it. But I stamp most of it, and then I do give one signature. But it's made my life a heck of a lot easier. Anyway, on that note, any more questions?
Nope.
All right. So I go to the question for you, Jolene. You feel like you're getting it? Am I explaining it in a way that you're getting it?
Yes. So I'm understanding the principles. I'm understanding what happens to your body. If you throw me out those questions to do the math, I'm probably not going to pass the class.
Don't worry, I'm right there with you.
Good news is you won't. I want you to concept. You don't have to memorize the math, so you're good to go. Dallin, how do you feel like you're understanding? Or you feel like you're getting a better understanding of diving?
So I'm with Jolene about getting the concepts, but as far as the math, no.
Fair enough. And we can work more on the math if you'd like. The good news is truthfully, there's only a couple of formulas to remember. There really is to really do this. And I'm trying to, of course, now.
Well, if we start, when we ask the question, if I could take the time to stop and dissect it and go back, then I can usually figure it out. But put on the spot in a minute, no.
Sure.
You give those to Dawn and Dwayne. Give the easier ones to Dallin and I, and we'll all be happy.
Exactly.
Absolutely. So overall, if you can remember some simple math, 1.4 and how to figure out the ATA, the rest is pretty easy, right? And it's just really simple algebra that solve for X. So partial pressure and the pressure of the nitrox or the pressure of the depth. It's all you got to remember. It's a lot simpler than you might think. If you can remember those things, the rest of it's pretty easy. Cool.
You could do it.
You can. I have faith. Don, how are you? Are you thinking you're picking it up and what I'm putting down?
Yeah, I'm picking it up just fine. It took me a second to figure out like your sack tank conversion there. Like I was working on it in the background a little bit, but I think I've got it now. I think I just didn't. You gave us that 50 psi per minute sack rate for that one example, and I tried using it, and then I was comparing the answer I got from that to what you were suggesting that your sack rate might be, and it wasn't lining up. But I think I've got the math right.
Yeah.
It was kind of a high sack rate for some like.
Oh, it's
50
incredibly high
PSI.
sack rate. I use it because it's easy math, but in terms of real world practical application, what you'll typically find on an 80 cubic foot cylinder, your average person should be around 14 to 20 psi per minute is a typical. A really good sack rate will be 10 to 14 psi per minute in warm water. On a dry suit on an 80 cubic foot cylinder, you'll see a sack rate somewhere between 14 to 25 is a pretty typical on an 80 cubic foot cylinder. So in terms of real numbers that you're looking at, those are pretty fair real numbers. And if you were to convert that to liters, typically you'll see the average student will be somewhere between 16 and 22 liters per minute on a warm to mid-warm dive. As it gets colder on a dry suit dive, you'll see more like 20 to 30 liters per minute on a dry suit dive. Those are more typical. So when I tell you Nikki and I are down to 8 liters per minute, that's a kick-ass sack rate. But I promise you, it's something that I work on every single dive. When I get in the water with you guys, I practice my sack rate. When I go out and do my own dives, I practice my sack rate. When I'm open water diving, I'm constantly thinking about it. If you guys would like a nice, fun, little easy video on this, let's see, youtube.com. I happen to have one. In fact, I'll share it. It's a 2-minute. You guys want to watch a 2-minute video? Let's see. You guys up for a 2 minutes video?
Sure.
All right. Let's see. You can go to YouTube. And if you go to Teach Me to Dive, let's see. Down here, I've got diving concepts. The second one in right now is this one right here. Let me maximize this for you. 2 minutes and 22 seconds.
Are we supposed to be hearing it too?
Can't hear it?
Can't hear it.
We can see it.
Okay. Well, I'll tell you what. You guys should have access to the chat. Can you guys see the chat?
Yeah.
Yes.
There you go. Click on that link, and that is a 2 minute 22 seconds on how to improve your sack rate and how to breathe more accurately during diving. There are at least 1 to 2 tips in there that I promise you will not find in your book, and are not in SSI. So there you go. There's some other cool videos in there as well that you guys might like. I've got yoga breathing. We've got profusion, diffusion. So there's all these are helpful videos about diving. So there, I try and build videos that are around 60 seconds. Breathing I couldn't get into 60 seconds. It's 2 minutes. So they're good little videos. How to break down a concept of diving in a short amount of time. So if you guys are into that, there's some tips and tricks for you.
Gotcha.
Easy enough. All right, guys. What else can I help with?
I think that's good.
All right, guys.
I've got a quick one or two.
Oh, sure. Go.
So I know that with partial pressure oxygen, even at 1.4, there's like a time limit because you're going to start to accumulate like oxygen toxicity units. But is there a similar thing that happens with nitrogen? Can you only spend so much time at like a certain like partial pressure of nitrogen? Do you get any sort of addition there?
That's a great question, and the answer is no. The effects of partial pressure of nitrogen at too high a partial pressure come to at a point. Once you hit that point, that variation is different for everybody. Your reaction to nitrogen is different than my reaction to nitrogen. And I go back to my statement about Sheck Exley. They actually studied him and determined him to be excessively resistant to the effects of nitrogen. I think he was just a big drinker and used to being drunk all the time. So just kidding. I think he practiced a lot is really what it came down to. So there's not a chart or a standard that I can put out for you that says, here's how long you can stay at 100 feet on air before you're going to go into narcosis. It's a very low studied field and has a very low study effect on it because the only place you can study it is at depth. So there's not a lot of information on it.
Right. And then secondary to that, is there partial pressure for some of the other breathing gases like helium that would be considered toxic or dangerous?
Yes. But it comes not from the toxicity of the helium itself. It comes from the partial pressure of the oxygen because helium is an inert gas. It doesn't cause a problem. Where it starts to cause a problem is when it gets too heavy. When you start getting too deep, breathing gas has a density to it, right? And when that density goes to a point where it's 6 times greater than atmospheric pressure is when it starts becoming more difficult to breathe and can cause high pressure nervous system disorder, which is a shake disease, confusion, things like that. And so it's one of the reasons that helium is nice is because it allows you to get to a deeper depth before the weight of the gas becomes too much for you to breathe, and it starts causing excessive lung strain. What most people don't realize is that you go down to 66 feet and spend an hour at 66 feet. That's like running 8 miles or brisk walking 8 miles. Your lungs are working harder, whether you realize it or not. You're breathing a heavier gas. If you're breathing a heavier gas, your circulatory system's working harder to accomplish the same goal.
So if we just
so the heavier the gas, the harder your circulatory system is working.
Gotcha.
There's a neat study. You should look up use of hydrogen in deep water diving. There's some really interesting reports and studies. They just did some more additional studies about 3 months ago in Hawaii. Hydrogen diving. It was extremely interesting. I really enjoyed those articles.
Okay.
But they're studying it mostly for extreme deep water diving.
Awesome. Cool. That clears it up for me.
Cool. Dallin, you got any more questions?
Not tonight. I'm good.
All righty. Jolene, Dwayne?
We're good. Thank you.
All right. I'm going to end the recording, and I will see you all tomorrow.
All right. Bye-bye.
See ya.